Welcome. Thank you for coming to the server engineering workshop session. This afternoon we have quite the lineup. So as mentioned before, we're going to start off with the Open Cloud Server version 2 overview, followed by another alternative system on chip implementation that we can put into the Open Cloud Server. Then we're going to switch over to the OCP mezzanine. This is the V2 mezzanine that's been going through the server committee for quite some time. Now we'll get an update there, and Mellanox will give us a presentation on the Connect X4. After that, Barrel Eye. You know, how do they come up with these names? This is a pretty Barrel Eye. This is a pretty cool offering with rack space and IBM coming in and presenting open power and bringing open power, a new high performance instruction set into the OCP. And then characterizing server performance. It's how do we do certification of components, and with this presentation is focusing on memory DIMMs and how to certify that. And then data center as a platform. We'll have a presentation on that last presentation today. So tomorrow we have a number of Open Cloud Server presentations, and Wednesday is a focus on the one-socket system on chip systems by Facebook. Both the real deal versus just the specification, as well as an example of a multi-node platform. Okay, so the Open Cloud Server V2, a year ago we brought in version 1, and we donated it to OCP a year ago. Last fall at OCP Europe we announced version 2. So there's probably nobody in this room that was at the Europe presentation. Or we do have one gentleman who was at Europe, and but nobody else was. So let's give you an overview of this. So it's a 19-inch rack standard. So basically in the server committee we've got we now have primarily a dedicated 19-inch rack standard on, as well as the open rack. And so it's a system that's designed, it's essentially a chassis system, 12U tall. You can hold 24 different types of blades. It is a blade server, and it's highly configurable. So you can put in storage nodes, JBODs, you can put in compute nodes, mix them up, any way that actually suits your needs. So we made this system to be cable-free, just like any other blade server, because we had a lot of experience that there are a lot of no trouble founds in our data center. And many times the solution for fixing a no trouble found is to reseat cables. So we had that issue. And also, especially when it comes to storage servers, we have a bunch of SAS cables coming out. The technicians will go off, they'll do service on these storage servers, and maybe 1 out of every 10 or 1 out of every 20, they'll go and they'll plug the cable back in wrong. The software will go through its checks and say, hey, you got to go back out, you got to touch it again. And so we try to keep from touching cables. So that's a big goal there. The system that we announced, the V2 system, is essentially compatible with the V1 system, but we've done some significant upgrades to it that will give more about that. Inside of the chassis, we have systems management. We have a systems controller in the back. We have what we call a REST API. Think of it as an XML-based interface. You have securely go in, you can do commands. We also have a tool that can be a human interface. People like me can type XML very well. but the native REST is designed for machine scale um, machine scale management. So interfacing that into tools. And inside of the chassis, one of the big issues that we've had historically is, well, people say, well, it's not Ethernet, it's just management, right? People get that cable wrong. You can always cable that wrong. And so we have this hardwired baked into the backplane. We said, and also we said, it's just management, just make it simple, very simple. So we run serial commands down to the blades to talk to BMC, and we run an on-off switch because sometimes BMCs hang. And in our experience, something bad happens in the data center. Usually it's like some sort of big power glitch and something really bad happened and the entire colo kind of glitched for some period of time. And then we have technicians running out and reseating boards because the BMCs hung. And but we said, let's just do simple power on off. Makes the entire blade go dark, just as if you pulled the power cord from the wall, and that effectively resets everything. And so we made that as part of our normal operation with our tools to do the full power cycle, because then you always get a nice clean boot.
Just to mind if I
Yep.
ask
Oh,
questions?
sure. You can ask questions.
On the REST API, is the plan to adopt the redfish spec for that, or is that already made it for that?
So the plan for the redfish. So we are doing a redfish demo, that sort of thing. So with the REST API, I think they may have to make some changes to work with redfish. I should be able to speak more eloquently to that, but my counterpart, Butterdine, has been in charge of all that. But so yes, we are working with redfish.
Okay.
So, and I believe we'll have a demo up on the floor of it.
Great.
So that is actually one of the really exciting things, to try to get these manageability specs to get aligned throughout the industry, so we can see more adoption of tools and more robust offerings there. So the upgrades that we did. Wow. Last night I worked on the slides, and what was on the right, I moved to the left.
Must have been late.
Yes, it was late. So what other changes did I not make? Okay, so let's talk about the chassis. So we have this basic 12U chassis. Basically, it's two flimsy pieces of metal that bolt into a rack. I call it flimsy. They're actually strong, but this is not a traditional chassis. So if you take you like your server chassis or even some sort of blade system, you can set it on a bench, plug it in, turn it on. This thing will not stand by itself. It requires the rack as structure. And so we wanted to minimize the amount of metal and that sort of thing in the system. And so we rely on the rack. So what we did this time was we said, hey, we need more power in the system. So with the new processors and that sort of thing, we have a much higher power requirement. And so we went off and said, hey, we need a 1600 watt power supply. But along with that, we now have what we call local energy storage. So you'll see up at the demo floor, we'll actually have one of these power supplies, 1600 watts, and got lithium ion or lithium polymer batteries embedded into it. And so I'll talk a little bit more about that on another slide, but it's very exciting. So what it allows us to do is to go to we can run blades average power over 300 watts. The previous version V1, we were really limited to 250 watts. And if you wanted to go above 250, you have to start depopulating slots in the chassis. So now we're well over 300 on average, which covers everything with ease. We added 40 gig Ethernet to the system. So the mezzanines that we had defined everything, was all set up for 40 gig, but we only ran 10 gig in the previous generation. But the cost of 40 gig has come down, so we jumped on it and moving everything to 40 gig. We have a slot in the back for PCI networking mezzanine. That's new to this. It's new to this. I believe we have we do have a prototype networking card that'll be up on the demo floor. That but basically it's a slot. You can custom create anything you want to go in there. So we have a full by 16. We run we allow it to be bifurcated. You could do 4x4s, 2x8s, or 1x16. So we did that. We're trying to think about what do we need to do for flexibility for the future, because we were thinking, well, we could, like these one-socket servers we were talking about, we could put 4 one-socket servers on that, or who knows what you could do. So a lot of flexibility there. Now the blade upgrade, we're moving to the latest Intel processor. That's the 2500V3, commonly known as Haswell. It has 36% more performance than the previous generation. So the previous was an Ivy bridge, but we were using the lower power version of that. So we went to a higher performance socket. So it's got more memory channels. We have a lot more flash. So we find our applications inside of Microsoft going all in on flash. So we have 4 times the capacity of that than what we had before. Again, the 40 gig networking, and we've plumbed this for 12 gig SAS. So 12 gig SAS is here, and it's time to switch to that. So,
Question.
Sure.
PCI Express pricing.
Yes.
That is standard form factor slot. Were you talking about pricing?
So it is a unique connector. So we attempted to use the open rack connector and mezzanine, but it didn't fit in our chassis because its form factor was more long and skinny. Ours is wide and shallow, and it's got a the Santec connector, but basically it's a mezzanine that plugs down. So it is a unique. So sure, yes.
You were mentioning simple processing, like we have been having a lot of issues sourcing that for how to simple processor or
Well, you'll see in the next presentation. So in the committee, Facebook has brought through a large form factor. They took the microserver and they made it taller, and they put a second set of connectors and more power and that sort of thing. They've got a server or a spec that's capable of holding some of these higher performance processors. So the original microserver could only take maybe a 30-watt CPU, but the new ones can be higher wattage. And so we're actually building a spine that can accept that. That you'll see in the next presentation, where we can plug multiples of those in. We aren't talking about the server boards right now. We're talking about the infrastructure that can accept them. For these are all 2 sockets, and if you tried to run it as a single socket, it probably wouldn't be. Yeah. Oh yeah, to get more drives. Yeah, no. So we have not designed anything like that or submitted any specs like that. So I understand. So when you get into the storage servers, you're getting so many cores on these processors, you don't necessarily need 2 sockets anymore. Yeah. Yeah. Well, here's the upgraded slide. It looks like I kept both slides in. It was late last night. So one thing I wanted to point out about the flash memory is that, yeah, we have slots for 4 SSDs in the front, but these cards, M.2 form factor, I'll have another slide on this, but it's this skinny little stick that's made for laptops and that sort of thing that we are embracing into our system. So we can put 8 of those cards onto this board, and the result is 4 times the memory capacity. Okay, so looking at the chassis again, I said, it's just, the chassis is really just 2 pieces of metal that bolt onto the side rails of a standard 19-inch rack. In the back, we've got a power distribution board where we plug in 6 power supplies. So these are the local energy storage power supplies, 1600 watts, that share power across all of the blades. And so you can set that up in, basically we have 2 basic configurations. One is what we call an N+N, where you bring in 2 PDUs and 2 sets of power supply, or 2 sets of power cords. So you have 3 power supplies off of one cord, 3 off the other. That only gives you 4,800 watts per chassis. Our normal configuration is that we just run single corded. So we run a single PDU down there, and we run what we call N+1. So that gives us 5 power supplies worth of power, which is 8 kilowatts, I believe, worth of power with an extra power supply in there for any sort of failure. Along with these higher power blades, we needed more fan power. And so is a combination of, we have higher power processors. We're doing 120 watt processors versus V1 with 95 watts. We have more DIMMs. We have 16 DIMM slots instead of 12. We have 4 SSDs instead of 2 SSDs, and man, those SSDs just block the air like crazy. And so we needed higher performance fans. So if you look at it, if you're someone like me, you say, okay, what does that mean? Well, that means that your fan, instead of being this thick, is now this thick. So it's got thicker rotors on it and that sort of thing. So, but that allows us to continue along with our strategy with N+1 fans. So single fan fails, machine keeps running, and let's see, there's our fan tray there. So one of the things that we did, we continue to carry the strategy of the fan door is the basic replacement. So you can go to the back, open the door, unplug the cable, just pick the door off, because it's not bolted in or anything. It's just resting on pins. Slide the new one in, plug the cable in, close the door, and the machine continues to operate. And so what we found was there's a significant cost to putting in individual hot plug fans. And so we said, let's just do this door method. And in our environment, many times when a fan fails, many of our groups just say, let's just schedule that to be repaired. We don't really need to repair that right now, because they say, what are the odds of a second fan failing? It's pretty low. Pretty low. It's not 0. And they say, well, if the second fan fails, what happens? Well, you may have to shut some servers down. They're like, yeah, okay. As long as the odds are really low that doesn't happen, that's okay, because our services will fail over to another machine somewhere else. And down at the bottom is this a picture of the power supply, but the servers themselves all sit. Oops. Let's get my sequencing. So the chassis manager, we have an x86 PC sitting in the back. Sitting in the back of the machine. We were on server 2012 on this, and this is this is what, we have Ethernet going into it, serial for like digi management, that sort of thing. This is what runs our REST API interface, and this takes care of everything inside of the chassis. So it'll take the commands down to the blades. It'll go to the blades and ask how much fan power do you need, or how much fan speed. It takes care of the cooling. It monitors the fans. It monitors the power supplies. Keeps track of everything. So the servers themselves actually sit on top of trays. So we have 12 trays that go into the chassis. We have a tray backplane at the rear where the cables, like our 40 gig networking come out, but that also distributes the power and the management throughout the system. So the local energy storage power supply, this is one of our big contributions. The specs are out on the wiki already, but this is a big deal, and we'll have a deep dive on this tomorrow. So essentially, what you do is you take this huge battery room, and you just distribute the batteries all throughout the data center floor. And as I said, we have N+1 or N+N of these things. It's really expensive to have multiple battery rooms, just for backup. So what we do is it's actually a lot cheaper to actually do this inside of the chassis itself. And so we take this across. So because it's distributed, we have N+1 or N+N. It's a highly available solution. So any single failure is like no big deal. It's just like swap out a power, same service as a power supply. Just swap it out and off you go. It is also very efficient. So the power that it takes to recharge one of these, we minimize the power. And so when you compare it to a data center with centralized UPSs, in those, I think a traditional data center, the percentage of power that you consume is really high, but we actually do very efficient UPSs. It's about a 13% overhead. Like your power comes in from the utility, about 13% of it is dedicated to backup. Well, when you go to the local energy storage power supply, only 4% is dedicated to backup. And so this is it's primarily just the charge rate that you need. After you have an outage, you need to dedicate some power to recharge these batteries. So so what we see is an efficiency gain by 9%. And to us, what that means is we can put 9% more servers into a data center than we could before. And the costs are not, it's all over the place. So typically, when we look at our data centers, about a quarter of your footprint is battery room, which you don't need anymore. So there's a lot of building costs that get saved. There's other electrical gear that gets saved. These static transfer switches. And, these are really expensive things. Because when you're talking about switching power over at the megawatt level, it's expensive gear. So it's all gone. Yes.
Do you power the network so you don't care about the network state?
So
The network switches up on the whole chassis.
yes. So currently, the question is about networking. So currently, the networking is off the shelf and does not run off of this version of the power supply. So that's something that we have to solve with other UPS equipment, but the networking does have to stay up and running. And so it's something that as we go forward, we will build, we'll get the features into the networking switches also. My notice is essentially aimed up more. That's better. Okay. How am I doing that timer? I should have coordinated this ahead. Okay, 15 minutes. Okay, so looking at the V2 blade, so the Haswell processor, 2600 V3, is 2 sockets. We support 120 watt version of this. So previously we would only go up to 95 watts. There's 16 DDR4 DIMMs, half a terabyte of memory off of that when you get to the 32 gigabyte DIMMs. So storage, we have 4 hard drives in there, and you can either put in 4 SSDs or 8 M.2 cloud SSD modules. And so we have a section up here that we dedicate for if you need SSDs that gets plugged in there. But these M.2s, we sprinkle them all over the server. So we have these risers with 1 on each side of the riser. So 2, 4, 6, 8. So we try to find spots anywhere where we could find a spot. We put those in. And in the I/O, we have a networking card. This NIC is also a custom mezzanine. It's got a connector in the back here that the networking plugs in here, and the network signals come out of this this connector in the back.
Are you using it?
Well, this is an OCP. Well, it's an OCP mezz, but it's different than the open rack mezzanine. So this is we've contributed this design in the V1, and in the V2 we made it a little bit bigger. Again, everybody needs a little more real estate.
Is there a reason why I can normalize all the design?
Yeah, the other design is a very different form factor, and it's designed. Well, the other design is actually intended to be on a server where the cables go directly into the server, and this one's designed for blind mate. So this guy actually has a 40 gig and a 10 gig running down through the motherboard to go out, and so you need that for the blind mate functionality. So we have 2 different places that networking can be, but this is the preferred one that we run. Again, we did a 12 gig SAS. On V1, we actually had a SAS card that plugged in, very much like this. But what we found was what we really wanted to do is we can put in a slot. We have a slot up here where we can put an HBA into the card, and then we run cables back to a couple of headers that run the networking out the back, and so those connections are now ready for 12 gig. So spending a little bit more time on these M.2 flash cards. Again, you'll find these cards. There's a whole set of standards around these. I think they go all the way from 30 millimeters in length to 110. We support 3 different lengths, 60, 80, and 110 millimeters. So we've donated the specification for our what we call the cloud SSD, okay, and that's the specification for this card. These risers, this is just one vendor's representative type. You can see can be set up to support any of the 3 different lengths. And so the card, in many of today's laptops, these M.2 form factors take a SATA interface. Okay, the industry is transitioning to a PCI Express interface, and so PCI Express-based flash gives you lower latency, higher performance, and it enables a NVMe-based native interface, which is defined by the PCIe SIGs, and is very high performance. And so that's where server flash is going. That's the future. And so we've enabled this. We'll use AHCI, which is basically enabling a PCI Express device to look just like a normal SATA device, or the native NVMe. When we go vertical on these devices, so those big, the big 2.5-inch drives, block the airflow and they're really clunky and that sort of thing. Well, you know, we're looking at same capacities on this long little stick, and we can put in 8 of them. We turn them up, and the thermals are much better. So when you plug in, you know, even if you did apples to apples, you did 4 SSDs versus 4 of the M.2s, you would find that your fans in the system would actually run slower because you're not blocking all that airflow. These things look a lot more like DIMMs from the viewpoint of the air. And so in our specifications, you'll find that we have both a low endurance and a high endurance version. So the low endurance version is just like putting any old client-based SSD into a server. A high endurance version is for those applications that, of course, do a lot more writes, and they have things like power fail protection and all those sorts of goodies in them. Oh, who is the vendor? So I don't know if we're talking about vendors, but basically everybody is moving to this.
Yeah, I know, but currently we have a
Yeah, so I don't know if we talk vendors, but I think we've got some samples up in the. Martin, do you know? Are we talking about vendors? When we look at the roadmaps, each of the big flash vendors has this on their roadmaps, and they're all coming out. You know, basically this year, this calendar year, they're all coming out staged in time. So. Yes.
So you mentioned power loss protection. How are you addressing that?
So the power loss protection, part of it is run in the controller itself. Part of the hardware is a bunch of tall caps on the back. So when we have the power loss protection, we find we actually violate the PCIe SIG because it's taller than those caps are taller. That's okay in a server because you got a DIMM, you got plenty of room around it, so we allow these exceptions. But you know, it's the circuitry looks just the same as if it was a 2.5-inch SSD. You know, they just packaged it in a different format.
And so you're basically trading off density to get power loss protection in the 20-point heads. Is that how I should interpret that?
It doesn't really.
Real estate that would otherwise you can't flash or.
You know, I suppose you could recover some of that space and maybe put down another chip. But what we're seeing is basically interchangeable. You know, if you want a 480 gig SSD, there's a 480 gig M.2. If you want a 960, there's a 960. So they're basically matching. You know, so yeah, you know, I think it could be accurate to say that we went from 80 millimeter to 110 to make sure that we can support all this. But basically, they're just interchangeable from capacity. So, okay. And, oh yeah. When you look at 8 of these NVMe based drives compared, there's lots of goodness. You know, capacity's 4 times. You know, the performance is just amazing. When you go to the NVMe with the PCI Express by 4, you know, 29 times the performance of 4 SATA-based SSDs. I mean, it's just, that's the future.
One was using
This SSDs, 2.5-inch form factor SSDs running off the processor chipset. And if you look at the processor chipset, it was running 4 hard drives and 2 SSDs, and it's got a skinny little pipe from the processor chipset back to the processor. So here also you get the PCI Express directly off the CPU right into the main complex.
Where do you find I mean, I know you don't talk to specific vendors, but the cost of these and M.2 versus regular systems is comparable? For gig or-
So as any new technology is transitioned, you know, you see a transition in costs, but because of all of these benefits, you know, the industry will transition to this, which means the costs will transition as well. So it's all about volumes, right?
But the NAND itself is the same, so I assume that the cost differential.
Yeah, it's not much. So pretty comparable.
So since the density is small, since the size will have limitation. How much gig do you have?
Well, 1 terabyte now, or this year. You know, so the density pretty much just follows the flash, and so you can get these 2.5-inch drives that are like dual PCBs that can get you to double the density or double the capacity, I should say, in a big fat SSD. You know, but that's like putting down 2 of these sticks, because you got 2 of those guys, and then you're still running it through a skinny little 6 gigabit link. You know, that's not that skinny.
Since you use the MEME, you don't care the latest machine or you don't have the density.
Oh, yeah. All of our drives are direct attach, single. You know, we don't do any SAS, dual ported SAS. You know, master failover. You know, primary, secondary. We don't do any of that. Talking about the backplane, this is our upgraded tray. So our previous tray, we had power, we had dual 10 gigs, and we had like a dual 6 gig SAS. And this is half of the backplane, and this is the second half. So what we've added is a PCI Express by 16 to talk to the mezzanine card. So I showed one mezzanine card plugged in here. And we converted one of these 10 gigs into a 40 gig, because we're looking at what is the transition. When we built this machine, we said, okay, we're on 10 gig now. Somebody, you know, 40 gig is coming, but we don't know exactly when. And but basically 40 gig is here. And so in the so this card itself is passive. There's no active components on this card because it's part of the chassis, and it's not easy to replace. And so we had to have it to be very high reliability. And so the card itself is, you know, in the back. It provides all of this connectivity. And then this is an example of this mezzanine card. So this is yet another form factor of mezzanine card, which we really didn't want to do, but we needed something skinny. We have a very deep rack, and we couldn't make the chassis any longer. So, so we had architected this. Basically, we said, okay, we're on 10 gig. We see 40 gig coming. Now the 25, 50 gig stuff is just around the corner, but that stuff can't go through all these connectors. Okay. We're going to have to put something back there so we can plug that 25, 50 gig in directly. So we architected and we said, yeah, we'll put that spot there and we'll see when we need it. And that networking is coming into the industry. So so you probably see something eventually coming there.
So
Yes.
this card, what exactly is to the right of it?
Yes, so this takes the by 16 for the blade on the right side, and it goes, so just like here, it goes to this little mezzanine connector, and that's the input. It's actually the same connector, same physical part number that we use on the blade for the networking mez, but on the blade for the networking, we take a by 8 PCI Express up, and then we take networking down. Here we said, well, we're just going to cable straight out, so that's how we get the bicycles to go out. Okay, chassis management. I must be running close to overtime. Oh. So our chassis manager, it's an x86 PC. We're running Server 2012 inside because we like all of the features that you get with Server. You know, we have a TPM on there, Trusted Platform Module, get secure boot, and all that sort of stuff. And then we run the chassis manager service on top of it as just a normal service. Like if you have a Windows-based PC, you go off and look at your services, just another piece of software. So we didn't want to be doing embedded firmware and all this sort of stuff. It's a lot easier to write an application that goes on top of an operating system. And so what we run is serial, a simple single transmit receive down to each blade, and an on-off. Chassis manager also takes care of, you know, again, all the fans and the power supplies. You know, and we have open sourced all the software and everything that runs on this as well. All right, a little bit more on the networking. So if you look at the motherboard, this is the networking MES. So we actually, on the V1 networking, we actually had dual 40s coming out of this because we thought, we don't know what's going to happen in the future. Let's just define dual 40s. But what we got was vendors coming back saying, hey, we need NCSI, which is a sideband management protocol. We're like, well, we only do serial, but you know, if somebody wants to build in sideband networking, that's fine. So what we did was we repurposed 3 of the channels that would have been 40 gig, and we said, okay, it's a 40 plus a 10, and then we took these 3 channels and converted them into NCSI. That's in the spec. We don't deliver that ourselves because we use our serials, but that's fine. So if you look at the paths, this is our mezzanine connector on the motherboard. It goes back to an AirMax BS2 connector through the back to the QSFP and the SSP Plus. We have a retimer on the motherboard for the 10 gig because on V1 we put a retimer there because we were being very conservative. We didn't know if this networking path would work. With the 40 gig, we looked at it and we said, why add all the costs? And oh, by the way, these retimers were designed for 10 gig, not 40 gig, and it wouldn't work anyways. So we did the signal integrity analysis, and it's fine. So we run 40 gig just fine off of that. So, of course, we only take it up to 3 meters. V1, we did a JBOD, 10 hard drives with an expander. We have 8 lanes of SAS coming out, 6 gig. We've architected this. The new backplane support 12 gig. We did not change this design, but it's 100% compatible. You know, you plug this into a V2 backplane. And just a quick pitch. Safety is a huge concern. We have data centers all over the world with all sorts of jurisdictions. We have to operate safely, and we have to meet all compliance. So, you know, not just shock and vibe or, you know, make sure that the machine can be transported, but, you know, standards all over the world. I think we're about out of time. So there are software submissions. They're talking more about this. We have the Chassis Manager V2. We also have Operations Toolkit. So one thing we found after joining OCP is that people are having a hard time actually utilizing the machine. How do you run them? So we have tools that we use in the data centers that we've outsourced as well. So there are a series of PowerShell scripts, you know, firmware updates, diagnostics, you know, just running basic stress tests and that sort of thing. And you know, There was another big item here for chassis manager service V2. Oh, it's not even listed on here. The serial sessions, we only supported one at a time. Just didn't have the software ready. We now support, I think, at least 8 through the chassis. And the other thing was originally we only did our management over Ethernet, and people said, hey, we need this serial, call it Digi, but these serial concentrators, we should have that. So we added that. And lots of contributions by the team. So a number of other presentations that are going on, and you know, I don't want to cut into our next person's time too much. So I think I thank you very much for your questions along the way. We're out of time. So thank you. So for this session, we have Bruce Smith here from Microsoft. He's a principal architect involved in our server infrastructure team. Here to talk about the SOC systems that we can install in the OCS.
All right, thanks, Mark. So, as Mark said, so this is really more of a preview, if you will, of a project that's in flight at Microsoft related to this kind of emerging class of processors. And so what you'll see later on in the week here, when Facebook has a couple of presentations, hardware and management interface presentations on Wednesday, that really get into some of the details of this one-socket server design point. There is an active link now for kind of our preview version. It's under review in the specs and server design section of the website. So you can go there now and get a lot more detail and be all ready to ask the Facebook guys lots of questions when they have their presentation. So as Mark said, the genesis of this format was what used to be a 73 by 210 millimeter card. Maybe you could do 75 watts sort of with that design point. Really targeted at maybe like a 4 to 8 core kind of atom processor sort of design. So now this new format, it goes up to 160 millimeters, and while the spec is being written at a little higher level, we think we could comfortably handle 150 watts on one of these cards. So that really opens up the possibilities for this sort of design point. So some of this now, so Mark went through a lot of detail in terms of the tray backplanes and lack of cables and having this kind of hot swap capability and unique form factor mezzanine cards. Well, this is a little bit different. So if you compared this to what Mark had just gone through, when you look at the back, so this is a tray here, right? So this is no longer 2 nodes that fits into this tray structure. Now everything's on the tray, and instead of the tray backplane with the rear cabling, this has a very small card in the back, which just goes into this power distribution board, and it picks up 12 volts and makes the serial connection with the chassis manager, and has like 1 or 2 other signals, on-off signal and effectively a throttle. So So the design point here is that these one-socket nodes, and we can support 4 of them in a tray. The constraint is really in the direction of towards the edges of the tray, since those are 160 millimeters tall, and there's 2 of those, and then this spine in the center. You have to have a little bit of room in order to just get the things out when you need to service them, right? So that kind of sets the constraints for the width of the tray sets the constraints. This is all in a single 1U, by the way. It's not pluggable. It's from that perspective. The design point is completely instruction set agnostic, right? So the interfaces into the node are very standardized sorts of PCI Express and Ethernet and whatnot. And the management interface is very, very simple kind of SM bus protocol, really a proper subset of IPMI 2.0 with a few OEM commands sprinkled in. There's a serial console to interact with the processor on the node, and then a couple of very simple control signals like throttle and on-off, that sort of thing. So there's nothing there that ties it to any particular sort of architecture, if you will. The power interface board, again, picks up the power from the power distribution board in the back of the chassis. And then as compared to the standard server nodes, the communications here is using the version 2 of the OCP MES card. And you also notice that this is front cable as well, right? So there's several, this is kind of a iteration, if you will, of this sort of design point. And then there's one board that's in the center, which ties everything together, and we just call that the spine. And so it supports the connections of all the nodes, the OCP MES cards, and power. Yes?
So basically, the MES card is inside the 1S node, then the network adapter, is it inside the 1S node?
Well, it could be. It could be, because the MES cards can support like a 10 gig KR. So you could have a NIC essentially on the one socket node, or they also support they support PCI Express.
Is it the same card that's now being used in the current design?
It's the V2, so it's yeah. You'll see. I have a block diagram on the spine, and you'll see it does have maybe a wrinkle or two in that design that we take advantage of. So you appreciate our highly detailed drawing there on the side. But anyway, so this is kind of the raw card for the spine as we see it today. Little bit of ocean front for some LEDs and push buttons and things like that. And then this, so the new one socket format has essentially 2 mechanical PCI Express by 16 connectors for each node. Right? And these are actually straddle mount connectors that plug in this way. So the boards are all coplanar. Then supports 4 per tray. There's some PCI Express connectivity that goes to the OCP MES cards in the front. And then coming off of the second connector is a dedicated by 8, which will go to connectors on the spine that we can use for the OCP cloud SSDs that Mark talked about earlier. So on the node itself, we could expect probably 1 SSD and then 2 more on the spine. And we'll also use that connector will also be like a standard by 8. And so you'll see from the block diagram that if you wanted to do like some debug and plug in a video card and a USB and a SATA drive, you could do that for each one of the nodes that's in the system. In a bench kind of arrangement, right? It's not a production kind of thing for that particular element. So we drive USB and SATA off off of the first connector to some dedicated connectors on the spine. Then there's a BMC, and it fundamentally functions as a tray level BMC. So it connects to the chassis manager. The chassis manager from the get-go had the kind of logic in it for 48 nodes in a chassis. So you think of this from an overall chassis perspective with 12 trays. Each tray has 4 nodes, so it's 48 basic servers within that same construct. So for this tray BMC, it captures a serial interface, the SM bus from each of the nodes, and then parses those, or sometimes it will forward serial traffic, obviously, to the chassis manager. Other times it's more of an intermediary when it comes to IPMI, in that it'll get some sort of request from the chassis manager, and then it'll parse that out to whichever node is of interest. Or it can also act on its own dependently. So there are some ID bits associated with both the nodes and the MES cards. So if desired, you can do a match to make sure that you're not plugging in one card that expects PCI Express and the other one needs 10 gig KR. So you can do some level of configuration verification if you want to. There'll be right at the like at kind of the top of the picture there'll be a ambient temperature monitor. I know each of the nodes also has temperature monitoring, but you'll see when you look at the way that the nodes kind of get populated into the spine, what might in some systems be a ambient air sensor is really going to get hot air off of the exhaust of the node in front of it. So we'll have an independent sensor at a tray level, and there'll be some LEDs to help if needed for manage to say which of the nodes might not be healthy for some reason. Though in general, these kind of data centers, you really don't want to have anyone have to walk out somewhere and look at some LEDs to figure out what needs to be replaced. Right? They should already know well before they can. So each of the nodes will have a going out power distribution into the node will be controlled by effectively a hot swap controller. So you can turn off all the power to a node if desired. And you can also monitor the power of each individual node from a tray perspective. And then the tray BMC also has connections back to this power interface board, which has its own hot swap controller, so it can keep track of all of the power in the tray at any point in time. Yeah. They're not hot swappers. No. Yeah, it's on off, and hot swap controllers have a PM bus, so it makes it very easy to capture power and energy measurements. Right, yeah, it's really more power control. That way, it's kind of the same concept as the chassis manager being able to shut off the whole tray or a whole blade. That if some portion of the node hangs and you can't communicate with it, then there is one way to take all the power off and turn it back on. I'll show it when I get.
Is there a way to toggle power just for one tray?
You can toggle power in each node individually. Yes.
So you have 4 or 5 hotspots.
Right.
Oh, okay.
Yeah, I mean, you could probably, definitely, you could do that in a little bit simpler manner by just having a FET. So, but having the ability to capture the power with the PM bus is kind of nice. Okay, and then one of the big things here is that from a systems management standpoint, this is really just it's an iteration above what we have in a two-node kind of system. You know, we have 4 nodes, right? So it's really using the same established protocols that are already in place today.
Question.
Yes.
Yes, fine. Previous slide showed plus global power. The lens part of global power. The 2.3 volt requirement. 3.3 volt also.
Yeah, there's the V2 MES spec has a number of different power.
Yeah, is that also
bands.
like fine from?
Well, the spine will have to generate that in order to provide it to the MES cards, yes.
Okay.
Yeah. So, I mean, this is not the most detailed block diagram ever, but give you some idea of how these parts interact. And it's just a few things to point out here. So where you see the by-8 PCI Express and the SATA and USB connectors, so each node has that same different group of connectors associated with it. So, and the SATA and USB really are more for a debug sort of scenario, bring up defect isolation, that sort of thing. It would be highly unlikely that these would be deployed with drives actually attached to those interfaces. Mainly because the by-8 PCI Express gives us support for 2 M.2s and then probably another one on the nodes themselves. So you see the MES cards in the front. The interfaces between the nodes and the MES cards can be PCI Express or 10 gig KR. So the MES cards could be a collection of small NICs. Could be an FPGA that does bump-in-the-wire encryption. Could be a number of different sorts of implementations there. When you look at the power interface board, you see these 2 red power connectors. That's really so that we can simplify the design a little bit of the spine and not have to have so much copper routing power. You know, not having a connector, just one connector makes that just a little bit easier. The BMC will be in the back there somewhere, and then there's that little block with local VR. So that's all the voltage regulators we need for all the different items that are on the spine themselves in the MES cards. The nodes will have to do their own power regulation down from 12 volts fundamentally.
Each one of the MES got 8 X.
Pardon?
Is it 16 X on the PCI or 8 X?
Well, those are, so the by 16 are like the mechanical by 16. I think it's actually like a by 12 on each one. That is in the specification. What we'll be using is a by 8, two by 8s, one in each connector.
Is it one MES card?
Well, you could do one MES card for 4 nodes.
All wired together.
Right. Yeah, that would be, so the simplest kind of implementation would be if you just had an FPGA and did like a bump-in-the-wire encryption, something like that, right? 10 gig KR coming off of each node. Because these are even in the near term, these one-socket nodes are not going to have really the same kind of network requirements initially. Right, so 10 gigs is probably good for now.
But basically, the KF.
Right. I mean, that's one approach, right? Or you could have PCI Express and have multiple NICs, or I'm sure there'll be other implementations going forward. So this might be a little too detailed, but so anyway, this is a power interface board. The gold tabs that you saw on Mark's tray backplane before are on the left-hand side here. Some are 12 volts and ground, and then a couple of signals. And the signals, there's only really 2 that go all the way through to the nodes, and that's the UART signals that go to each of the tray BMCs, and then fast throttle it's I actually probably called something else in the current spec, but it's an indication that there's a power event and you have to take some action kind of quickly in order to avoid any sort of shutdown. Really, the size of this card is going to be gated by what's on the right-hand side, which are a bunch of beefy connectors to deliver, up to 650 watts to the spine. You could imagine perhaps that. So you can probably get reliably 160 or 70 watts through those pair of connectors for each node. If there was a situation where you wanted to deliver more power to the node, then we'll have a couple of extra connectors, kind of like GPU style, where you can just bridge additional power onto each node. Since this is not a hot swap scenario, then we can do those kinds of things. And then there'll be some local voltage regulators here for things like disk drives, in the debug scenarios.
Question on the
Yeah.
you have a I'm assuming problem like the final regulator.
Yeah.
Have one regulator shared off with another.
Well, that regulator would only be there for like disk drives if you were doing had some disk drives that were part of your debug setup. Only 12 volts goes to the nodes. So no, the 5 volts is only there for convenience. That'll be developed on the spine itself, not here. I mean, you could argue, okay, that 5 volt regulator, you wouldn't even populate it in production. It's there for convenience and manufacturing support.
Trying to understand a scenario that part of the node
Yeah, that'll be a bit of a challenge. Yeah, that particular scenario will take a little thought. Make sure that we get that right. It's a little different when you think of the M.2s, right? So those are only associated with a particular node, and also the USB and SATA. So, but the shared resource there, yeah, that'll take a little effort. Good catch. So not too much else there. And so this is the hot swap controller for the whole tray. Right? So this is, and this one really is a hot swap controller because you can take the tray out to service it and then plug it back in. And it also can give you a complete tray level power dissipation. There'll be a lot more on this between the pitch that Facebook is doing and also another Microsoft presentation. But it's essentially the notion of having the single management controller that's on the spine. It connects to the chassis manager via the established protocols, which is mainly serial in the case of cloud server specs. And it's extensible. It's going between the management controller and the nodes. It is a fairly straightforward sort of interface with a serial port again, SM bus, and just a couple control signals like throttle and power on off. And that's about it. So the particular management controller that we're starting with on the spine really just supports 4 nodes. It's got 5 UARTs, so you can have one for each node or one for the chassis manager. But there are management controllers or other implementations that can support more serial channels. And so that's really the primary thing you have to do is to be able to support additional serial channels. The expectation on the node side is that there'll be some sort of small management element. It's really a small subset of IPMI 2.0. There's not a lot that it has to do, and in fact, it could even be sort of more or less a bridge function. Or in the future, if there's SoCs that have a management controller that's part of the device and it's on a completely separate power rail, then you could say that that's not even required. It can just be done by the SoC itself. Another reason to have it kind of separated at this point is that when you first gate 12 volts onto the node, you want to keep the power dissipation kind of at a low level, right? So we kind of allocate about 5 watts, give or take, to that management controller function. And maybe if you had like a wake on LAN sort of thing you wanted to try to implement, you could do all that within a 5-watt budget, I think. So this is kind of what we're envisioning for a typical node. And again, this is in roughly in this kind of 150 watt power envelope sort of thing. So you could allocate. This is assuming you have some reasonable amount of memory and an M.2 and probably not much else. You could allocate maybe 100 watts plus or minus to the SoC. And I kind of use that term loosely because you could say, well, I want a 50 watt SoC and a 50 watt FPGA attached to it or something. So like I said, it's not. There's no instruction set affinity with this design point. So you can do conceivably do a lot of different sorts of implementations. The node will have some VRs as required and it definitely needs this kind of 3.3 volt aux so that it can power up its management. From a packaging standpoint, you could probably 8 DIMMs is the most rational kind of limit to fit on that card. And then whether it's 4, 6, 8, it just depends on the particular design point. SoC. We would want to continue supporting the same cloud SSDs, so there'd be one, expecting to have one of those on a typical node. And besides meeting all the specs that Mark talked about before, the cloud SSDs have an elevated temperature spec, which, as you'll see soon, will become kind of handy. So there'll be 4 Gen 4 interfaces nominally that will be supported. You can communicate with the MES cards or the M.2s, as we've shown earlier. And then there's some miscellaneous I/O, USB and SATA drives for purposes primarily.
A curiosity question on the power. So you said you have 6 by 600 watt power supplies for the chassis, right?
Yeah.
Which would be 200 watts per SoC board. Why the discrepancy between 250 total node and 200 watts?
Well, so I think that we really get, 8 kilowatts, right? If you're in an N+1 kind of environment. So I think we can probably do 650 watts. I think there's gonna be thermal and power delivery kind of challenges, right? For both. So just in terms of if you have kind of back-to-back 100-watt processors, then that takes, you have to, and you want all the parts to be kind of identical. Then it takes a little bit of effort in order to do that. So that's kind of why one of the reasons for around 150 watts. But I think if you take 650 watts times 12, you get around 8,000 watts.
If you do 8 kilowatts, I just said 8 kilowatts divided by 12 divided by 4 is 167 watts. But there's fan power that.
Yeah, and there's also the cloud SSDs. If you have a couple of those for each node, and you need to allocate maybe 20 watts, or portions of 20 watts from the MES cards, it all adds up. That's why I said it's not like a hard 150 watts is an absolute hard target, hard spec, but I think it's around there in this design. So when you look at some of the things to examine from one of these one socket nodes, and just talking about the 150 watts. So from a thermal perspective, in this kind of 1U envelope, you get about 60 CFM, which is, it's not poor. It's pretty good, right, for a typical 1U server. Nominally, you don't like to go, way over that, because then the data centers could eventually have some issues. The cloud SSDs, as I mentioned, 85 degrees C spec, that helps quite a bit, because when you look at the way that the boards end up being configured, there's kind of like nowhere that you can hide like lower temperature components unless you put them where the DIMMs are probably going to be, because you really want the DIMMs to be kind of in the, in line with the airflow. So you could put the cloud SSDs there as well and cut back on the number of DIMMs supported. So maybe 6 DIMMs in the cloud SSD. So there's a lot of room to balance that around those points. And I should stress too that what we're really focused on in Microsoft is more like an infrastructure for these one socket, or emerging kind of one socket designs that we see. Not necessarily so much, except to say, hey, we really like our one socket nodes to look sort of like this. They're not necessarily something Microsoft's going to directly develop. So when you look at it from a heatsink standpoint, and the amount of room that you have both above and below the spine and then the coplanar one socket nodes. So you can think of it pretty much the same as a regular 1U. There's, unlike the blades that go in, there's not an extra layer of sheet metal. So you do have really pretty much the full 1U. You just have to, and you need to account for a little bit of the fact that maybe the tray above, moves ever so slightly. But effectively, you have a 1U design height for your heat sinks and all. So I think that could be pretty helpful. High-speed routing will be sort of interesting, particularly for the nodes that are furthest away from the OCP MES cards, obviously. So that's an area where, but when it comes to both power delivery and high-speed routing, we're investing some effort up front in order to do simulations of both from a power integrity standpoint and a signal integrity, to make sure that we're providing a proper environment, if you will, to communicate between the MES cards from the one socket nodes. And if it means that the material of the spine has to be improved a little bit in order to really facilitate that, then certainly that's what we'll do. But so it's one of the areas where having a group that develops surface products and comes in pretty handy, because we can go to this kind of common group within the company and get that kind of support. Yep.
Are these connectors 8 volt connectors?
Well, they're standard PCI Express connectors. Yeah, they're just straddle mount, like, instead of pin and hole or surface mount or whatever. So this is a highly detailed drawing here. Anyway, the point of this is that there's going to be some flexible options, because the design point is moving to. And that's one of the things that in the Open Compute server design today, and I think I was keeping track as Mark was going through his presentation, and I think there were 3 or 4 questions about the form factors and all of the different mezzanine cards. So this is more. The focus of this design point is more on providing this tray and the spine and the infrastructure and the communications with the chassis manager and getting all that down, as opposed, and then leveraging other elements, the one socket node that's going to be discussed in more detail later this week, and then the OCP v2 MES card, which I think there's a presentation right after mine on that topic. And so the target at this point is that we expect to get hardware in the next few months and be in a position to have a more thorough set of contributions related to the spine and this sort of one socket tray in the fall of this year. So today was really intended to be just a little bit of a preview and kind of a, here's a kind of directional sort of thing. But there'll be a lot more detail as the design point solidifies. Any other questions?
You showed 4 nodes of SD. What's the mechanism of sharing SD card?
Well, it depends what exactly you want to do with the mezzanine cards. Let me go back a little bit. So you could, so it could be, so there's different kinds of interfaces that you can drive off of these kind of one socket nodes, 10 gig KR or PCI Express. So it could be either one. You could drive, say, 10 gig KR and have an FPGA that did, bump and wire encryption, for instance, if you had 10 gig support on the nodes, which could do. Or you could just have a fairly simple means of maybe having like 10 gig NICs, that are pretty cost, size effective these days. And literally have 4, or I could envision some other technologies being available that could lend themselves to this in the future.
So the follow-up question then, if the 1S node incorporates networking, for example, on the SoC, how is that network exposed outside the chassis?
So an even simpler case would be that you could have a PHY, you could have a quad PHY on there, and so these MES cards are front cable, so you escape the chassis out the front.
So you have like a null MES card in that case?
Well, it has to have a PHY at least, at minimum, to go from KR. Yeah, you can do that, sure. Any other questions?
I'm not sure this is even a correct question. So because I haven't seen the 1S notification, is it only Arduino supported, or is it supported without Arduino and some other format?
The current design really is targeted at SODIMMs, but this design can support any sort of regular Arduino.
Including the Arduino, because
it's really a function of what the SoC itself supports, right? Mechanically, and so you have a certain amount of power, and if you want to allocate more of it to your LRDIMMs and have a whole bunch of memory for your processor, you can make those trade-offs. Okay, thank you.
Just a little bit ahead of schedule. For some reason, I think, Bruce, you must have been wondering why I kept thinking I was running out of time, but for some reason I thought I had 45 minutes, so I guess that was good, then I didn't run over an hour. So, I saw our next presenter come in and then he left. He was here. He'll be back, so,
You don't want to take a short break, maybe have someone coming in, that's the presentation.
yeah. So we'll resume at 2:45.
I'm a hardware engineer in Facebook, and Jacob, thermal engineer with Facebook. And today we will give an update for what's the update on mezzanine spec from 1.0, which was released last year, which was released actually 4 years ago, to 2.0, which was released last year, and what has been the change after that today. So first is some background. Maybe just do a quick survey is how many of here are from Nick vendor, like certain kind of Nick vendor. Okay, yeah, thank you. Good presentation from one. Yeah, so I hope this session will be helpful for the Nick vendor that plan to implement OCP Mass, and for the system vendor who plans to implement a system that will take the OCP as form factor in terms of what's a feature, what's a change. So first is some background. So what's showing here is a example implementation of OCP Mass 1.0. So sometimes it's also mentioned like Mass 0.5. So pretty much the same thing here, not very exact term here. It's developed in 2011 for the what we call as accelerated implementable E2 for the OCP platform, and internally we call it windmill. So it supports like two SAP class for 10 gig Ethernet typically, PCIe by A for the host side, and has a measurement on I2C. So it was to address a certain system configuration back then, and later during the years we see the challenge in different areas, such as what kind of I/O it supports on network side, what kind of interface to the host side that this stack can address, and what kind of thermal limitation it has. So we see those challenge, and so that we work on a spec that to address that challenge. And the spec was published last year, and through the feedback from the community, and we get voted and passed the OCP incubation committee in August. So what I'm showing here is the key changes from our key features from the OCP Mass 1.0 to 2.0. The blue fonts here are the changes part from 1.0. Go ahead. Your mic. Okay. Sure. Probably that. Better. Maybe I should just talk to you. Yeah. So the blue part are the one that's specifically for the OCP at 1.0, and in the I/O side, it has QSFP in addition to SAP class, which is at 1.0, and also recent we actually added QSFP 28 into a draft, which is not sent out to the community yet, but should be sent out very quickly. On the host side, it extends the PCIe by 8 to by 16, and also added the NCSI interface in addition to I2C for a higher throughput for the management. And it supports the KR to the host to expand the use case especially for the SoC that may come with internal NIC that need a KR mask. And also it provides two different types of stacking in addition to the typical 8mm stacking that defined in the OCP Mass 1.0. In the following slides, I use 3 different kind of boxes to show what was the in the stack that voted last year, and what was changed since then to deal with the problem we see or the challenge we see in the past a few months. And the last one is more talking about future plan, what kind of issue we haven't been addressed, but we are thinking a way to address. So quick refresh of since the last summit in Europe, there was quite low attendance. So I still have some material is about what's changed from OCP 1.0 to 2.0 at the point that last August, September-ish, to highlight what kind of change it is. The first is physically, we do some form factor change on the horizontal plane. And what you can see here are like a few big area colored differently or in different kind of box. So the first is everything not in the solid line or the dashed line. They are the OCP 1.0 mass, like mechanical. If you look it from, I think they look it from bottom to up, like you, if the car is facing down in the system, you look at about this bottom view. And the first area enlarged is the dashed area on the right side. It is for accommodate additional width for the QSFP, dual QSFP connector. So it is enlarged in mass 2.0. And there is a dashed area in the left. It was a kind of a jumper in a motherboard, so we cannot have that cut off. But in OCP 2.0, we remove that kind of limitation. That we think the vending car going forward should not take in too much burden from one old motherboard. And on the top left side, there is a called optional area for connector B. So connector B is one additional connector to the motherboard, in addition to the 120 pin connector A, which was in the 1.0 spec. And on the upper right corner is an additional area for I/O to implement case such as four ports SFP plus or 10 gig XT. And to highlight here is optional area is really just for that specific purpose in order to have best backward compatibility, so that it shouldn't be used unless you are you have the need for a secondary connector or additional I/O space. So it's not for like place VR components to address such kind of problem. And one thing to mention is in the next slide we will talk about different vertical stack and all the optional on the horizontal placement applies to all three kind of vertical stack. So it's mix and match. And from vertical plane, what kind of vertical plane is you take a cross section vertically and you see from the front view of the system. And then on the type 1 is a typical step up with an 8mm spacing from the measuring card to the motherboard in the OCP MES 1.0. And the main reason driving this kind of variation is thermal. That in some implementation, we see more challenging thermal condition to meet the TK, so we need more spacing for the heatsink. So we define optional 12mm stacking as type 2. In type 2, the chipset is still facing down, and a type 3 is targeting for like those more thermally challenged design, which will have the chipset flipping up. Facing up, so it pretty much has a more, you can say infinite area to grow, but it will, the more you grow, it will more impact the system compatibility or config limitation. And feel free to tell me if there is any question. And on this slide, it shows the I/O side option getting changed in the OCP mass. A few examples are given for different I/O types. And this one is has been changed since the last vote and to the draft in my computer. So I want to mention here. So we do see the need for us to go beyond 40 gig, which can be supported with QSFP. So we are looking at a 50 gig and 100 gig solution. So we realize there that to support 50 gig and 100 gig, we need a 25 the line rate, and we need to upgrade the connector. So on the market, there are two kinds of connector that supports 28 QSFP, and one kind is like called EQSP from a Japanese vendor, and the other major like Monex typo, they are pushing for the EQSFP, which is very similar to the original QSFP, but it has a longer connector, so it also has a longer cage. So on the lower picture, you can see if a connector has a longer cage, you will need a larger cutout area in the motherboard if the stack provides so. So the plan for Facebook to move forward with this kind of connector is to allow to use both style A and style B. Also, style A is like the EQSFP, and style B is called EQSFP for trademark wise. to line up at the back so that our existing motherboard or baseball can take both connector, but the I/O side will be extending forward to accommodate the extra bank. And in the following couple slides, it's talking about the change on the interface to the host side. It can be a baseball, it can be a motherboard. So first is that we added NCSI single definition. That has been, all of these, I think, are in the previous release, so pretty much a fresh here. So added NCSI for higher throughput for OOB. We added thermal reporting interface for the baseball to be aware of how thermally critical the management card is running at. And we define four PCIe resetting, and also we added measuring card ID and baseball ID as a way for measuring card to sense what kind of baseball it's sitting at, and for the baseball to detect what kind of measuring card it's working with. Card ID is like measuring card ID is implemented EEPROM in the measuring card, so baseball can read it, and the baseball ID is implemented with the hardware circuit. There is an example of implementation following slide. And this is one of the change of the version 2.0 that we add one more connector. We call it connector B, and it's the same family of the connector as connector A, FCI bird stack, and it's 80 pin instead of connector A 120 pin. And mainly this connector is aided to get more bandwidth or more PCIe lanes or more KR lanes planned to the host side. And also to mention, it should be used as needed base. For example, if you are doing a by 8 PCIe card, you probably shouldn't implement extra space of the PCB and this connector, since that will cause backward compatibility with the existing motherboard mechanics. Here is a KRMAS. It's one new interface introduced to the interface to the host, and it was defined in the OCP 2.0 last year, and there are some change on it, so I want to highlight here. So the main change is if you do a KRMAS for, let's say, for example, 4 ports KRMAS, we change the pin where the KR should be come from for the updated spec. So we hope it doesn't impact any existing implementation. We have been working with the vendor we are working with for KR, and we manage that. So let me know if you are doing KRMAS, but somehow it's impacting your implementation, and I can explain in more depth about why we do this. So this page gives some change on the baseball ID, what it is, and what has been changed from last year to now. Baseball ID is for the baseball. can be available on some kind of wherever the measuring card goes into to self-declare to the measuring card side who I am. To implement in a way that it is a registered who I put on combination, and it will be it will take a measuring card to detect at the very power on the first 4 seconds of power on. The measuring card should finish all the latching or detection of what kind of baseball it is, and then after 4 seconds, baseball can toggle a GPIO and connect the pin back to the present pin, which was originally assigned. So it's multiplexed with the present pin, traditional PCIe present pin. And what has been changed from 0.4 to 0.45 is two areas. One is I had a miss of not considering the case for connector B, that if you are unpopulating this connector since it's optional, then on the measuring card side you will see a floating signal. So I require the measuring card side. If you need to detect a baseball, please it have a very weak pull. I think I put it like 1 mega to make sure it's not floating. And also more detail are added to the baseball ID table. So to be specific, what kind of register value defines what function in that connector, and there are a few value pairs are made for future use. But pretty much it has all the enumeration for the different combinations of those two connectors. And connector A and B have separate settings, so it can be mix and match. So it can be like a baseball have one kind of define on one pin. For example, you can have a baseball have a PCIe on one connector and the KR on another connector, or mix match. On the power side, I have some feedback from one ODM saying they have some platform that doesn't have power blocks. So I showed the history of what was the definition of 12 volt in the measuring card in the 3 different versions of spec. So originally in MES 0.5 it was put like 12 and 12 volts either way. Due to actually at that time it wasn't conscious because one of our VM implement as 12 volt and the other one implement 12 volt box. So we kind of asked the NIC vendor need to support both. So it's kind of a miss back then. So on the last version I corrected as like you have to be 12 volts since our system runs on 12 volts and supply the 12 volts to the measuring card by default the way we want. And for measuring card, we pretty much use it in the NIC, which we want to have access at all system power status. And the feedback comes from MDM that, for example, there are some systems such as Catholic, I think, it doesn't have a 12 volt box, which is more of maybe a traditional single box power supply, or some system has 12 volts, but it has very limited current or power to be used at NIC. So I think I take that feedback and put back the 12 volts in a way that people can still implement a measuring card in their specific system with different assumptions at Facebook, and have enough power. We'll say to allow the 12 being non-auxiliary. But it puts some challenge on the measuring card vendor that you need to consider the system that can run a 12 volt and 12 volts on those power rail again. And one suggestion is you may if your rails or if your power is running under I think about 12 watts ish, that can be taken from 5 volt aux. So we have 5 volt aux defined, and it's 2.4 amps for 5 volt. So you may take like majority of your power there, and some of the power from 3.3 aux or 3.3 volt if needed. But if it is still not enough, you may consider doing a diode OR, like your VR takes both 5 and 12, so you take a diode OR from 5 volts and 12 volts, so whichever have a higher voltage will deliver the power to your car. So for baseball, I put a requirement and it's preferred to use 12 volts. Like, I mean, you don't use 12 volts unless you cannot. Measuring card, you may choose to implement either way, but if you support both, it would best compatibility to the baseball. All right, so we'll get into the thermal topics, and I will do the first slide and pass to Jeffo for the simulation side. So one change has been added is we added the thermal reporting interface on the 2.0 mass, which is the last year. So this part we haven't been making any change, and it has been working out well. And the thought is we need a specific way to let measuring card vendor to report its critical temperature to the system, so that our fan speed control can take it into algorithm and monitoring. So there are two ways of implementing it. One way is if your main IC has an internal thermal diode, like the lower picture here, you may put a TMP421 types of thermal sensor with isolating interface, so the baseball can get information. Alternatively, for some IC, it may internally do some sensing, or it may sense more than one points, that it may sense multiple points in the car and decide which one is more critical, or either one can be critical. Then we suggest you implement a way on the upper right corner, which use a so-called emulated method. So what does that mean is that you expose a register, I2C register in the format of TMP 421, and there is more detail in the spec of how the standard TMP 421 register that you need to support for this implementation, and some other like device ID type of requirements. And I will pass to Jacob for the remaining part.
Thank you, John. So today I'll talk about some demo on the before I actually talk about, so today I'll be talking about how do we run the simulation for those. But before I actually go on, I just give a bit of background for I've been observing the last few months. So basically, over the last few months, what I've been observing is that our system simulations and the actual test report that I'm getting from the vendors are quite different. The reason is that our system simulations that can consider all the environmental conditions, while just the car itself, it doesn't really cover all the side effects, like bypass, or how much the CFM actually going into the car, and how much the bypass, and what's the local pressure, and that's all varied. So most of the time, it's kind of back and forth talking about what are the requirements, and so many email back and forth with the vendors, and there's not much conclusions at the end. So what we actually decide is we decide to look at our system and run multiple simulations within our system and come up with some general guidance how do we run this car simulation based on our system. So still changing on the specs. So we decide to remove the LFM requirements in the spec. We decide to to leave the key to the user to basically the customers define what's the LFM for that. But we will define what are the boundary we should be considering this. So generally, this is applied for type 1 and type 2 OCP 2.0. My simulations actually doing about 84 millimeter width, 4 millimeter height, 300 millimeter length chassis. That's basically our core tunnel. And we put the race car in the center, and I'll talk about some margin on the left side of the bypass. So assumption in the model is very simple. So we use open chassis on the both ends so that we have a one-directional airflow, and make sure the chassis is non-conductive, so there's no body version. And also turbulence, I use the automatic algebraic turbulence, and I also use the inflow airflow, which means that I put the flow in the front so that it actually blows the air to the car, not the second layer. So general rule is that first, for the length, I want to give it about 100 millimeters space between the inlet of flow and to the car. And I want to give it 3 millimeter on the side, each side of the car, and the car is placed on the center of the channel, and I want to give a 0.8 millimeter margin on top of the so 0.8 millimeter between the back of PCB of the mass car to the chassis. So my simulations not including any small components or 2.9 millimeter reserve spaces for the small components. So it's going to be just a flat PCB, nothing on the top. And from the top to the chassis is about 0.8. And just one thing that I want to highlight here is, so the reason I put the 100 millimeter is, to be honest, it's not really a matter. What I actually find out is anything above 50 millimeter and length is already clearing the boundary layer after that. So easily 50 to 100 doesn't really matter. So I get the piece. But with the 3 millimeter on the space on the car shows that it's simulating quite similar to the model you consider a lot of bypassing under the connectors, and on the left side of the connector, so that I get the very similar local pressurization within the car. And one thing to also another highlight is the connectors on the mass car is extruded to the chassis, so considering it actually sits on the model. Sure. Yeah. Any questions on the demo?
So, are you running thermals both forward and reverse airflow?
Yes, I actually did. It's the reason I actually put the inflow because when I try the inflow and outflow, I get the very similar results on the controller temperature, but not the temperature. The reason is that I guess when I put the outflow, it actually creating too much kind of bypassing. Like it's creating the boundary layer and also and bypassing. So the QSP temperature was a little bit off based on my simulations, and that's why I pushed the inflow. Technically, we're supposed to get a similar result, but unlikely that I didn't get quite the same result on the QSP, but I got the control temperature that's very similar to what I see in this system. Another reason I put the inflow because we put the cars in the front, and since the system actually sucking the air, but my velocity monitoring region was actually in front of the car, and that's why I want to look at that same LFN to the car itself, like the car simulation. So I want to apply the same velocity, and that's why I put the inflow instead of outflow. But
I think your question is, do we consider like reverse air direction, like from like heatsink to the because we take the doctrine of the air is blowing from the connector to the IC. Are you asking like, do we do the reverse way?
Right.
Yeah.
Is the reverse airflow for the OCP 2.0 is not considered here. The reason is that we have all the I/O is on service. We have all the cable actually connected on.
Yeah.
And
But it's put into an OCP
Yeah.
platform.
I think to the point that that the message we have here is like we want to define a kind of we want to define a method that first will accommodate our assumption, but I think it will be a quick tweak to make because we don't have the criteria. It's just a simulation method or testing method. So we can also define if you put the car the other way or you blow the air the other way. And the criteria is up to specific systems. Say, if I use this method, what will be the airflow, what will be the inlet air, and what will be the airflow. So I think it will be a quick trick to accommodate like that kind of frame and let the system vendor to
I mean, as a job point about, I think the way that simulating methodology should be the same. With the reverse airflow, definitely we get a different result because of the QSP will be preheated by the controller, and then the temperature is going to be different. So from that perspective, I think it's going to be different.
Was there another question?
Yeah, let's talk about how you're using it.
I'm using photon simulations.
Okay, so are you planning to release the required source? You do have photon.
Share the model.
Yeah.
I guess we can release the model, but some of the detail on the vendor specifics should be.
Like some of the heatsink maybe we use one vendor heatsink, I think we may move it, but I think
This is this.
like for example the chassis dimension, that kind of thing. No serious problem. So we are over time a little bit here, so just really quick for pointing out what has been what will be need to be worked on. For the last one is the thermal specification that we need to put in spec in a way that everybody, most people agree on those message. Other than on the KR side, there was some question on the loss budget from one of the tech vendor that we hope to put in, but I don't have that data. I haven't get it done yet. And then the second one is for sideline for KR. It's probably better to put away how to drive the LED since we don't have the LED pin defined on the connector. So just want to highlight what's missing here. So any other question in general? Okay. Thank you.
Jealous of. Okay, I'm jealous of Jaws hoodie, but at least I get to put this on. So I'm Kevin Deerling with Mellanox Technologies, and I'll talk a little bit about our contributions today. But first of all, just wanted to give a little background on Mellanox for those of you who don't know the company. We were founded in 1999. We're about 1,600 employees. We're a public company, traded on NASDAQ. So it says NYSE here. We're an end-to-end provider of interconnect solutions. So really silicon adapters, next switches, state-of-the-art Ethernet solutions, dominant supplier of 40 gigabit Ethernet adapters. And we do cables, QSFP modules, copper, VCSEL, optics, and silicon photonics. So a little history about our contributions to the Open Compute project and our activity. Starting back in the 2011 timeframe, we did the 10 gigabit version based on our ConnectX-3 silicon of the OCP adapters. In 2012, we added UEFI support and also the mechanical adjustments to provide for the triplet servers. In 2013, we added functionality with our ConnectX-3 to do shared NIC functionality. And then last year, we did the first 40 gig OCP MES card with our ConnectX-3 Pro device, which is shown up there. And then we also did a switch design specification of our 40 gigabit Ethernet with 36 ports, as well as with breakout cables to 4810 gig or 1240 gig switch port. We've done ONI and SAI contributions. So that's another thing that was mentioned today in one of the earlier sessions, is that the switch abstraction interface, we'll be showing that tomorrow at our booth. There's interoperability there, a Microsoft operating system running on a Mellanox. So we announced that earlier. Now we're actually showing real implementation. It's our SAI with the Microsoft on top, and we're interoperating with other switches, so there's multiple switches out there. So 2015, we've got now the announcement of 25 gig, 50 gig, and 100 gigabit Ethernet network capabilities, and our multi-host, which I'll talk a little bit about, and the OpenOptics WDM technical contribution. So this was a contribution that I'll also talk about that was made today and is now public. So just to get started, put a little bit of background behind why we're doing what we're doing and why we're seeing the evolution of the data center that we see and how that's dictating the network adapters. So clearly, we really live in a world of data. It's growing exponentially. There's more applications, mobile devices. Everybody's carrying around a cell phone that's generating huge amounts of data. And really, this data needs to be accessible always and in real time. And what we see here is that the data has changed from being slow and small to big, fast, real-time data. And this requires innovation in the data center architecture. And so we want to move so that you're not being buried in data, but you're actually able to utilize it, analyze it, and turn it into business value for the companies that are taking advantage of the OCP platform. So really what we see here is an evolution where going back, instead of a scale-up architecture, you did a scale-out architecture, really a multi-server architecture using rack-based servers. The next generation of that is really driven by Moore's Law, where you see multi-cores inside of the CPU. And now we have higher server density, and each of those CPUs has a lot of different cores in them. And really, the next generation of this is what we call multi-hosts, and I'll go into some details about what we're doing now. Fundamentally, what we're seeing is a change from a compute-centric architecture that was developed in the previous generation of really transactional databases, so that you were doing reservation systems and banking and sort of ERP systems, where it was a very compute-centric architecture with the CPU in the center and memory, I/O, networking, storage surrounding that as peripherals. And the data portion of this was really an afterthought. The idea of big data and unstructured data really isn't well equipped to be able to deal with this CPU-centric architecture and the compute-centric architecture. So big data is really problematic for those types of solutions. So in this new environment with social media, social apps, really it causes some changes to the way you think about building computer architecture. So putting the data at the center really changes the way that you can do the optimization of the network. So rather than being server-centric, you really become rack-centric and data center-centric. So what that looks like when you put the data in the center, you've got compute, networking, and storage, all three being really different parts of the overall solution with the data built into the center. So this higher level view of the data-centric data center allows rack and data center optimization. So instead of optimizing only at the server level, it really starts to look at the higher level of the rack itself as well as the data center. And you can start to disaggregate the server so that each of these elements, compute, networking, and storage, can scale independently from each other. And it really allows you to start sharing resources. sharing of your CPUs, storage, memory, and I/O resources. And the key to all of this is an intelligent interconnect that really is needed to drive the data efficiently between these different resources. So if you look at the technologies here that's required to make that vision a reality, there's really three different elements to it. First is sort of the server disaggregation that I talked about with resource sharing, and I'll show some more on that in a second. Second piece is efficient data movement. And here we use RDMA as an example, but I'll talk about a couple of the other things in there, which is virtualization acceleration. And the third piece here is high-speed data connectivity. This is copper, optical, and silicon photonics. And I'll talk about the silicon photonics piece today. There's another session that's going on later today that we're digging into details on that. So the server disaggregation is really enabled by this concept of resource sharing. And here you've got, multiple CPUs that are actually sharing the network connectivity. And this enables very efficient use of your network and compute resources and the efficient data transport that's available. So it also says that you can start to use single socket CPUs. So if you look at the various workloads here, many of these workloads are not actually using a single system image. So they don't need a large cache coherent interface to connect them. You can actually have independent processes, and of course each of the CPUs has many, many cores in it. So you're able to run those processes on a single CPU. So you don't need the large scale up SMP architecture. You can get away with the single socket CPU. And then you connect them to this shared network resource. I'll talk a little bit more about that. Gives you symmetric data access to all of those CPUs. So there's no difference in terms of the network speed connecting to any of those different CPUs. So it's not a NUMA architecture. It's a very symmetrical architecture. So the second piece that I talked about to enable this is the efficient data movement. And here there's really three pieces to that as well. The first is a technology that we have in our adapter, which is called eSwitch. And that stands for embedded switch. And what that means is, on the top, on the left there, you'll see there's 4 virtual machines. And those virtual machines can talk to each other through the eSwitch. The reality is they don't need to be virtual machines running on a single physical CPU. They can actually be physical CPUs. And the same technology of doing the eSwitch to communicate between those individual virtual machines or physical CPUs is used. And that open virtual switch, the OVS, which is what the eSwitch is basically logically a switch, just like any other switch. It can be a layer 2 switch, can be a layer 3 IP switch, and all of the same rules apply that you would use in a normal Ethernet switch. And you can communicate between those different servers, whether they're virtual machines on a single physical server or if they're actually different physical CPUs. You can use that same eSwitch capability to do that. And it's very sophisticated. So it's steering the flows to the actual processes. And the good thing is unlike a physical switch here where the resources are limited to whatever the forwarding tables are that are on that switch, in this case we can scale out to very, very large numbers of forwarding rules. We're actually limited by the server memory. So we have a set of resources that are on chip, and then we can go off chip, pull those data in. So we have a very, very large forwarding table at both L2 and L3. The second piece of this efficient data movement is actually on the overlay networks. So if you look back in history, the last 10 or 15 years was about virtualizing servers and creating virtual servers that you had VMs, and sort of VMware was at the center of that change. Now what we're doing is virtualizing the network itself. And we're creating overlay networks, things like VXLAN and NVGRE, and now Genève. And we support all of those and accelerate those so that you can take advantage in this new virtualized world, and you're moving virtual machines back and forth without having the application even be aware of that. The internal packets, the tunneled overlay packets, are actually keeping their virtual IP addresses and virtual MAC addresses the same, even when the physical IP address and the physical MAC address changes. And the third piece of this efficient data movement is a technology called RDMA. And RDMA is a technology that stands for Remote Direct Memory Access. It allows you to move data from one application to another application very, very efficiently with very low latency without using the CPU. So today we have that with both our InfiniBand products, but also with our Rocky at 100 gigabits per second. So the third piece of all of this enabling of this data-centric data center is actually very, very efficient data connectivity. And so today we made a contribution to the OCP, which was announced, and there's a presentation that we'll be talking about the details of that, but it's actually taking advantage of single mode fiber. So the single mode fiber has the advantage that it can travel very, very long distances, 2 kilometers, even more. And we do that with WDM technology, meaning we put different light colors onto the same single fiber, and we use that with standard QSFP form factors. So in terms of connectivity, we really believe in the spirit of open and OCP that these are standard form factors. So it's a QSFP form factor that's industry standard, and you can choose that for copper, you can choose that for multi-mode VCSEL-based solutions, or now you can do the single mode fiber, which is the silicon photonics-based solution, all on the same standard QSFP and all on standard fiber technologies. So go into the details. We'll publish the WDM for this, what's called the Open Optics WDM specification. The other companies involved are Oracle, Ciena, Renovis, Yazi, and one other who I forgot. So the other thing that we're doing is introducing our ConnectX-4 with our multi-host contribution. And so I'll talk a little bit about that in the context of the resource sharing that I mentioned before. So the ConnectX-4 was actually a product that we released back in November. We have silicon now, and we've implemented it onto the OCP 2.0 form factor, and we're launching that product. So this is a bit of a preview of that. The key capabilities here, you can look at it with InfiniBand, but the first generation we're introducing is the Ethernet. So it supports all the way from 10 to 100 gigabit Ethernet. This one is configured to support 100 gigabit Ethernet that's shown here, which is the QSFP connector. But we also support the 25 gig speeds and the 50 gig speeds with breakout cables. At 100 gigabits per second, we have application-to-application latency of less than 0.7 microseconds. 150 million messages per second. The technologies I talked about before, so the RDMA, Rocky support, multi-host technology, GPU direct, which I'll talk about, and overlay network offloads. So really all of this is now available in the OCP form factor. So the other thing, obviously, it's OCP 2.0 compliant. It's automatically self-configuring for both legacy as well as multi-host platforms. The host management support, so we have all of the basic host management support. If anybody asks me any questions on this, fortunately, I have some really smart people in the audience who are going to answer for me. I can't talk to this, but our baseboard management experts are here. So we can support multiple form factors here in terms of the interface. So we can do a single 16x PCIe interface. These are all Gen 3 interfaces. We can do dual 8x interfaces, or we can do quad 4x interfaces. So if you look at this in terms of flexibility, this can be 1, 2, or 4 different maps. And the interface there can get carved up so that you can build different systems based on this same single platform. So it's ultimate flexibility, and we're not trying to be prescriptive in terms of either how you use the device or how you connect it up. We happen to think that copper within the rack, the most cost-effective solution and the best power solution in order to connect these up. Similarly, on the adapter side, you can decide how you want to use this. We give you full flexibility, carve up the resource. So it's no longer just virtual maps. We're not just virtualizing, but also we're providing multiple physical functions for the same map.
Yep. Question. So in a scenario where you have 2 or 4 different processors connected using that multi-host capability, can you power cycle the hosts independent of the mezzanine?
Yes.
So there is complete isolation between the hosts. So you can reboot the power cycle of the software reset one server to not affect the other people.
With 4 servers, does it take 1 input clock to do 4 input clocks?
So if one goes down, you're not depending on that particular.
Does the OCP-Server Track have 4 input clocks?
Yes. Sorry, I think the thing. Oh yeah.
I told you there were some smart people out it because I don't know the answers to any of those questions. So if you look at the architectural changes that this enables, on the left you've got the typical environment where you have a one-for-one correspondence between the CPU and the NICs, 4 separate servers, that traditional design. Ultimately, you can connect multiple CPUs now to this single NIC, carved up PCI Express interface, and put that into a single chassis, for example. So the reduction here is both of the NIC, of the switch ports that you're using, and of the cables that you're using. And with 100 gigabit per second cables and connectivity, and all of the performance associated with that, you really end up with a very high amount of bandwidth. You reduce your cost of just the network connectivity by 45%. So that doesn't account for tsunami or something. So it doesn't account for the cost savings on the server platform, as well as any cost savings that you might benefit from in terms of being able to use lower level CPUs, single socket CPUs as opposed to dual socket or quad socket. Good. So there was some questions earlier in one of the earlier sessions of Microsoft, and I think this is shedding some light. So again, I'm not making any announcements here, but pay attention tomorrow, and you might see some announcements. And please come visit us in our booth, and I think you'll see some interesting technology that we're showing, because this is real, and we're excited about it. So obviously, you know, this capability here is really about scalable data centers. And frankly, I've been in the industry for a long time. This is the most interesting and I think potentially game-changing architectural change for servers in a long, long time. If I look at the last 15 years or 20 years of server design, it's sort of been about changing at 90 degrees. We started off with desktop servers, and then we went to tower servers, and then we went to rack servers, and then blade servers. And we're doing, you know, back and forth 90 degrees. This is fundamentally a new architecture that's really interesting when you start to look at what this is enabling. So we think it's very flexible, it's configurable, everything becomes modular, and we think it's a very interesting design capability that's enabled by this technology. So the direct connectivity lowers your OpEx, lowers your CapEx, you've got lower power, improved density, and really we think the smart interconnect is the core of enabling all of those. But the other key thing is that there's a tremendous amount of flexibility that's enabled by this architecture. Because from the standpoint of those connectivity, you've got 4 CPUs there. They don't have to be x86 CPUs, although certainly that's a viable option and it works. But you can use other CPUs. So I think, if you pay attention, I think there'll be some announcements from some vendors here at the OCP around the Open Power platform. And we were one of the founding members of that Open Power consortium. We support the Open Power architecture. We have other designs that support the ARM CPU architectures. So really, whatever CPU you want to use, we have the flexibility to do that. There's no changes in the software required. So when each of those devices, you could even have a heterogeneous environment with different CPUs if you wanted to do that. Beyond that, we can use not just CPUs, but GPUs. So if you have workloads, if you're doing machine learning, and you need a whole bunch of floating point operations, and you can use one of the advanced GPUs. You can even do FPGAs. So you can build an FPGA if you want to do some custom processing. So you could have, for example, 3 CPUs and 1 GPU. You could do 1 CPU and 3 GPUs. You could do 3 CPUs and an FPGA. And each of those has an independent view and basically is sharing that resource of the network connectivity. So it's really a flexible architecture that lets you take advantage of it the way you want to. So an example here is really going into the concept of the CPU and the CPU using a QPI interface between them. And then going to, in this case, we've just done two, so this could be two by 8 connections. Where now instead of being a dual socket CPU, you're using a single socket CPU without the QPI bus. So if your workload doesn't require the NUMA capabilities of that architecture, and as we're getting more and more cores inside of CPUs, you may not need that because you have inherent cache coherency within the CPU. And most cores today, most CPUs have 10 to 12 cores. There's not many applications that are written with more threads than that. So it really allows you to use a new price point, and you're not even using network connectivity now to communicate between those CPUs. You're using the E-switch that I talked about previously. And so it's not actually going out through the network. So you have the bandwidth then available on the network side without chewing that up. So multi-host and PCM, actually, Vadim, why don't you or Yuval stand up and talk about it? You want to talk about it? Let's get Yuval up here. Because I can talk about it, but anything I said is something that he told me. So.
It got me kind of surprised, but okay, let it be. So when you talk about managing a server which is composed by multiple hosts, you need to think about management, talking about BMCs. So we have an approach which allows you to choose your own recipe for addressing multiple host server, meaning that if you wish to keep a BMC per host, let it be supported. If you want to do the most cost-optimized solution using a common BMC to manage multiple hosts while behaving as multiple BMCs, we support it as well. For that, we have some proprietary technology which allows, while being 100% standard compliant with the existing NCSI standard, we allow to manage multiple hosts, if you wish.
So maybe a four-way multi-drop Dixie bus?
NCSI? No, you can do that on a single NCSI. If you think about it a bit creatively. So you can use a single NCSI bus and let it behave as multiple personalities network interface card, if you wish, in that sense. And the association of a particular management traffic to a particular BMC instance is done automatically. So the NIC can identify the particular management session and associate it to a particular host, okay, and associate particular management resources on chip automatically. So if you want to set a particular management path to traffic for a particular host, depending on different setting than for another host, you can do that. Okay? And let everything be still 100% standard compliant. Okay? Now, in having a system, when you have multiple hosts, you need to think about the global resources. We know, for example, that on WCS, you have the chassis manager entity, which manages all the slabs. You need to think about potential need to manage the common resources in such a server. For that reason, there is a fifth entity for management within that device, allowing you to add chassis manager entity on top of the multiple hosts. So for n hosts, we support n+1 management resources, all done internally. And we took it a step further, and NCSI allows you to use MCTP for management over PCI using VDMs or over SMBus, if you wish, and let you to migrate dynamically between those interfaces. In parallel to that, you can use NCSI interface. We allow migrating between all these interfaces, not only between SMBus and PCIe within MCTP, but you can also migrate between NCSI to PCI to SMBus, and you can do that individually for each and every instance. So one BMC can use MCTP over PCIe, another one can use SMBus, and the third one can use RBD at the same time. And they can migrate dynamically for each and every instance. And sometimes you wish to use minimal resources, like minimal connectivity, like SMBus, for example, if you want to optimize your system cost for pin count. And for that reason, we support even all the BMCs sharing a single SMBus together, if you wish to optimize your cost to that extreme. So any combination is legal, any migration is legal, 100% standard compliant, and automatic detection. Okay, any question on that?
And that submission is also happening this week.
Yes, and everything is being declared this minute. Right.
Great job.
Great. Thank you. So I definitely couldn't have done that.
Good job, Dan.
So really, just to summarize, we've introduced the next generation of compute and storage rack design with this new architecture and 100 gigabit capabilities. This multi-host is really key to the server disaggregation and the resource sharing. And it enables this data-centric data center that I talked about, scalable high performance for cloud and Web 2.0 sort of designs, complete flexibility. So we're not dictating, as you saw, either on the baseboard management solutions or on the connectivity, whether copper, single mode fiber, multi-mode fiber. We're not dictating a design to you, providing the flexibility even to the point of being able to use whatever CPU you want, FPGAs or GPUs, reducing the cabling and the costs associated with this and the switchboard count. So looking forward to this, encourage you to come visit us tomorrow and look for some of the other announcements that we'll be making. Questions?
I just was going to say that we would all like to thank our colleagues at Facebook very much for their partnership with us, the great input they provided to us to enable us to come up with this design. So I'd like to thank Harry and John very much.
Absolutely. Any other questions?
The new interface you have, how do you connect back to the latest 100 gig?
So the 100 gig Ethernet, I don't know if there is a legacy 100 gig Ethernet. You know, we just started shipping.
AR4 or AR10, sorry.
Yeah, so SR10, you know, we don't connect to that. So frankly, everything we're doing is QSFP28. We've jumped to the density. So I see what you're saying on legacy. Yeah, that is legacy 100 gig. In terms of power, I mean, it's just 10 by 10 gigabits per second. It's really hasn't had strong adoption except for a few small core markets. In the data center here, we think it's a QSFP technology for density, power reasons, cost, etc. And so I think others will probably build chassis that go SR10 to I mean, we can do that with connectivity just through devices that support 10 gig and devices that support 100 gig, but it's really a cabling option, I think, more than anything. But we're not today trying to support that. But here we think it's QSFP28.
So is it possible to consider AR4 connected?
Yeah, I think you can do an LR4 connectivity. I think that's just a cabling option. I mean, LR4 is with the, you mean single mode WDM?
Yes.
Yeah, you need to have a converter. You need something that actually had ports that were, but at a modular level, you know, you could potentially do that. No, the modulation is different in terms of, I mean, it's a WDM module with the LR4. So you need something that converted between that. So you'd have two separate, the only way to do it would be to have two separate modules. Go in one port through and then come out another. You'd have LR4 module, and then a QSFP 28.
All right. Can we have questions after this?
Okay.
Yeah.
Absolutely.
Yeah, Kevin.
We're going to have a quick break here and encourage your questions for Kevin and the other team. There's quite a few people here from Mellanox on that. And we'll be starting back up in about 10 minutes with the open power system barrel off. Thank you. Can you hear me? Everyone here? All right, my name's Norm James. I'm with IBM. What I'm going to present today is a OCP Open Power server. That's called Barrel-I. Just real quick on Open Power, if you're not familiar with that, I think Rackspace, Aaron from Rackspace tomorrow is going to talk more about that. But just at a high level, IBM opened up its high-end power architecture and has made it available in the market as an alternative to build servers from. So anyone can build a server out of power technology. They started a foundation called Open Power Foundation. It has some some of the core members, Rackspace, Google, Taihan, MyTac. There's about 100 members now. So, but again, I'm not going to go into too much detail on that. Quick background on the code name Barrel-I. It has a transparent domes and open. This is an open server. It's going to be an open server, so we had to have a fish with an open head. So that's where the name came from. So the contributors are Rackspace, a big part of this, IBM, and the Open Power Foundation. So the objective was to build a truly, totally open server where every aspect about it is open. All the firmware components are open source. The BMC code will be open source. The BIOS is totally open source. I'll talk more about that in a minute. All the programmable parts, all that source code will be out there. And all the mechanical board IP will also be free to use. So layouts, constraints, stack ups, circuits, everything will be open. So anyone can take this IP and just be able to build a server without any licensing problems. Real quick on the power chip that this was built from. It's Power 8. It's in 22 nanometer SOI. It's a Global Foundries technology. About 650 millimeters square, the die size. 12 cores. One unique thing, it has 8 threads per core. Some other highlights, accelerators, some crypto memory expansion accelerators, transactional memory. Has an on-chip power management, separate little microprocessor on chip for power management. I'll talk a little bit more about that in the open source code. It has a unique memory subsystem. It has memory buffers. They have the example here. This is an example for it. So these are the processor sockets, and then these would be the memory buffers. The DIMMs are around the memory buffers. So even though they're separate memory buffers, has fairly low latency, 70 nanoseconds latency to memory. Each memory buffer has 4 channels of DDR3 or DDR4, and you can do 1 or 2 DIMMs per channel. In this design, we did one DIMM per channel. The bus interfaces, we call it DMI. It's the high-speed interface from the processor to the memory buffer. It's 9.6 gigabits, a total of 115 gigabytes per second memory bandwidth from a single socket. So this has 2 sockets, so it'll be 230 gigabytes of memory bandwidth. Integrated Gen 3 PCI. It'll support up to 4 sockets, the SMP interconnect. And the SMP can do 40 gigabytes a second. It's 6.4 gigabits differential. We have this interface called CAPI, the accelerator processor interface, and this is what we call the innovation bus. So it's a direct path into the coherence bus of the processor. Its physical protocol is PCI, but that's where the similarities between PCI style. So you can do custom hardware, ASICs or FPGAs. There's a FPGA toolkit available to build from. The layer in the FPGA is called the PSL. That's just the abstraction layer, service layer. So you don't have to go implement that, and that's available to use. But the point is it's a very low latency, you don't have to go through the I/O stack to get to this. It's coherent, memory coherent, and you can end up, someone could end up build their own technology, own accelerator, what have you, and attach it to that bus. Tell me if you have any questions. So block diagram of a barrel eye. It's two processor sockets. It has four of those memory buffers per processor socket, and then 4 DIMMs per memory buffer, so a total of 32 DIMMs. The PCI slots, it has one full length, full height for a GPU, double wide GPU, 1x16 and half length, half height, by 8, and then 2 by 8 OCP cards on it. It also has quite a bit of storage internal, 15 2.5-inch hard drives. They're hot swappable. We haven't quite decided on the height of this. It's going to be something less than 2 OU, something between 1 and 2 OU, around there. But it'll be less than 2 OU. Yep.
How wide is the board?
It's a full width. Look, here it is. The board is a 380 millimeter long. So I'll show you some pictures of it here in a minute. You'll get a feeling for how wide it is.
Yeah. So the 230 gigabyte per second bandwidth, is it the aggregate between the two sockets? Or?
Yeah, that's 2 sockets. Yeah. Each is 115 gigabytes. Yeah, each DMI length is about 28 gigabytes. The processor feeds the directs the by 16 slots, the mezzanine, the OCP mezzanine cards. It also feeds one. We don't have a south bridge, so we use a PLX switch with all the miscellaneous I/O attached to that. You don't have to do that. There's no requirement to have a PLX, and we don't have a south bridge, so there's no requirement to have a south. We also use the A-Speed AST2400 BMC. We have all the standard interfaces that you would need to connect to an industry standard BMC. Any questions? So this is some renderings of it. You can see this is the board that I'm showing you right here. This is a hard drive tray that slides in that has the. I'll show you a little bit better view of that in just a minute. With the cable management arm. We do tap off of all 3 bus bars. They're independently fed to 12-volt planes inside the system, so they're not tied together inside their system. They're independent. Yeah.
So, for the override V2, the bus bar count are reduced from 3 to 1. Like, so do you see the impact to your system here?
Yeah, it won't work. Yeah, we're designing for this is for the rack space rack, which is 3 bus bars.
So this is because the density of the
all the memory and
what's the total power?
It's 800, 900 watts.
It should be paid for 1 bus bar. It's like 1.
That's a typical number.
Okay. Sure.
Yeah, you can see the bus has a power distribution board, the bus bar flips.
Another question is regarding to the bus bar. It seems like it's physically soldered down to the display. Is that right? That the bus bar cable is soldered down to the PCB.
Yeah, that's still being worked out. I'm not sure that's. This is just a photo. This is just a rendering, right? So it's not the real thing. This is still in concept phase, early design phase, I would say. So that's still being worked out.
Yeah, since we see the challenge of like hard disks, the one will have floating, that it doesn't have floating.
Oh, yeah, right. Yeah, probably need a little compliance in there, right?
Yeah, or some tolerance for
Right.
mechanical or during transportation.
Right.
We assert the force to the
Yeah. Let's see. Hot pluggable fans from the rear, pretty typical, I think. in these. Also, the processor and the memory complex is one board, and then the I/O subsystem is another board. Otherwise, you get two. The boards get a bit large, so not manufacturable. So this is how the hot swap hard drive tray works. Well, first, this is the Dell High by 16 full length, full high, the by 16 half length, half high by 8 and the two NAS cards, and then management and VGA. And then the hard drive tray pulls out, and you can expose all 15 drives, and then you slide them in from the side. That was the design point we chose right now to get this level of density.
So why the choice for 2.5-inch drive? Isn't it expensive for cost of product?
That was the requirement that for this particular product. Yeah. The TCO argument wasn't, cost wasn't the only factor.
I mean, the 2.5-inch hard drive. I don't mean SSD, of course, this is right size, but the hard drive, isn't it?
Yeah, it's higher per dollar per gigabyte higher.
But the reliability isn't better than the 2.5.
Then you get into enterprise class drives and that sort of thing. It's mainly for performance reasons, more drives. Questions? So real quick on the call it the Power BIOS, and you can see here this is out on GitHub, so you can go on it today and take a look at it. And there's documentation up there. You can compile it. There's instructions on how to compile it. We have evaluation boards today. If you want to play with it, you can get evaluation boards to play with the firmware BIOS. So it is out there today. It's essentially made up of three components. Host boot is the part of the code that initializes the chip, prepares the cores for the OS. Kind of gets initializes the proprietary interfaces, gets the chip up and ready to start. Opal is Open Power Abstraction Layer. It's a Linux-based bootloader. So once you're into this part of the BIOS, it's a Linux-based. So it's pretty easy for people to understand who have a background in Linux. You can script, you can create boot menus or whatever you need to from a Linux perspective. So it is the bootloader. It scans the PCI buses and presents the boot menu. So let you select the boot order or what you want to boot from. And essentially, when you're in that point of the BIOS, you can go to a prompt and do LSPCI and things like that. At that point, it is a true Linux operating system. OCC is the power management code, and that's that little microprocessor that I was talking about earlier that's on the die. And that's open source as well. That's what does the thermal monitoring, the power capping. So the thermal control loops are running inside of that. There's a template there that the way we did it. That's a starting point, but if you want to extend it, but it's what also allows you to go to push the frequencies up based on the environmentals. If it exceeds the temperature, it'll back the frequency down. So you can run different CPU governors in Linux on demand and performance, and that's what implements those governors in Linux.
Yeah, this is GitHub, but open power, not the OCP.
That's correct. Yes.
So what sort of software licensing?
It's Apache license.
Apache.
Yeah. The license, or there on each. There's basically, I don't know, different repositories. There's the github.com/openpower, and then there's the different repositories for the different pieces of the BIOS and documentation and some build scripts and the build environment. There are all these different repositories that you can independently clone, and then there's a license agreement, but it's all Apache license stuff. When you do the build though, it pulls in, I think, the Linux. We don't put the Linux distro on under our repository. It downloads that as part of the build process. I don't think that's all right.
Just some of the,
Yeah.
or is that also on GitHub?
No, that's still in the works on what that's going to look like. The goal will be open source, still being worked out how to bring that to reality. But that is the objective.
Board?
Yeah, this is a fake board.
I was
Showing
gonna say,
that,
that
yeah.
one looks.
Yeah, there's no
it's
wires or
a
anything.
slick board.
Yeah, it's you can see through it. There's nothing here. It was a fake board.
It's
Yeah.
mechanical.
Yeah. I had to cut it with my miter saw to get it in my suitcase. But the dimensions are approximately correct. 380 by 600. Yeah. Yeah.
A question about the drive or.
Yeah.
So we're not often, that's all being moved, but I'm curious about the other benefits that you mentioned.
I mean, because you want them hot swappable and you want all this I/O on the front, and this is, pretty short, so you don't have enough space on the front to put all these hot swappable drives, and the requirement was that they be hot swappable. So you really need some kind of internal thing like this. It's not fun, right? Because you need that cable management arm in there, right there. So it's not fun. It's not the cheapest, the least expensive solution, but you kind of have to do that though to meet this level of density and maintain the continuity. Right.
So those are all SATA drives?
There's SAS. We have a SAS expander. Yeah. In fact, there's not very well. This is again just a rendering, but somewhere in here will live a expander board. Yeah. Not yet. They will be though. They definitely will be. This is again early, and that's why I don't have a real board. But this is early in the concept. But yeah, the board files, the schematics, everything will be the schematic source, not just a PDF. The OrCAD source will be. I'm ask Aaron that. He talks for Max, so exactly.
For the documents or the designs, since you are this probably also part of the open foundation.
The designs will be released through Open Compute.
Okay.
Yeah, not Open.
You won't do nibbles.
I don't know. But the focus will be the OCP releasing of that. Yeah, Open Power is not intended.
No, I was more like if you are interested with kind of reading those like forums and how do you manage that?
I don't know. That's why I'd be worried about that. I think, to keep it simple, I would think release.
So,
Yeah.
this is a great submission and all this stuff, so when, at what point do we start seeing submissions come through the server?
If that's Aaron, that. I'm not gonna.
Okay.
Ask Aaron that. Any questions? Thank you, Norm. Yeah. That's not decided yet. It'll be somewhere probably just north of that. We're not sure yet. That's right. It's a little, this rendition is a little taller.
I know, I got to take. You got it.
Yeah. Yeah, this is 6. Somewhere in between. You want these better than well, forever. Also, well, it's the second. I have this. That's right.
This one over here says no signal.
Well,
We can move the camera if we have to.
yeah. said before, sometimes the box is kind of slow. Pick up. That's underwriting. Okay, I guess.
Or you can just tilt this one. Slide it back, tilt it.
So you actually get a free.
So what I just did enter the last one. Page up, page down. Okay, so you want me to start it? Oh, turn on my microphone. Okay, so I'm hoping everyone can hear me. Is it okay? Okay, great. Okay, so today I'm going to talk about some server memory performance and specifically characterizing workloads. My name is Barb Eichinger. I'm Vice President of Future Plus Systems, and so I'm an engineer by trade. I have a BSMSEE, and I've been doing memory for a pretty long time. And so I'm going to talk a little bit about characterizing workloads. So I'll go over the latest DDR technology, which is DDR4. I think most of you are familiar with DDR3, as you have DDR3 in your servers today. A little bit about the traditional performance measurements, some new performance metrics that we're proposing, and we'd like to see the OCP community perhaps standardize performance metrics so that then the T&M industry can provide a set of measurements to you that's an apples-to-apples comparison. I'm going to show you these performance metrics measured on a real-life system. Then I'm going to show you how I measured it, and then we can wrap up and take any questions that you might have. So DDR4, this is the 4th generation of double data rate memory. DDR, double data rate, just means we clock the data on both edges of the clock. It's just that simple. That's what the acronym means. So for DDR4, it's faster, all the way up to 3,200 mega transfers per second. So they use the mega transfers per second acronym because we're doing it on both edges of the data bus. So the clock is actually half that frequency. DDR4 has lower voltages than DDR3, so it's better for power management. It has some power savings features that I'll show you a little bit of, which makes it a little bit better for reducing your costs in the data center. Higher density is also being specified, specifically using a 3D stacking with a through silicon via technology, so you'll see that coming in the future. LR DIMMs, like you had on DDR3, we have LR DIMMs for DDR4, but this time around the data buffer is also there, not just the address command and control buffer that we had on DDR3. So LR DIMMs are used to put more capacity on the channel, on the DIMM itself, so you have larger capacity. So in general, DDR4 is more robust. It has an alert signal for ECC errors, and also the command address bus is covered by a parity. So it's a little lower voltage, it's more robust, and it's higher bandwidth. So a little bit about traditional measurements in the industry that you would look at when you were characterizing a workload. You might look at bandwidth, command bus, and data bus bandwidth, power management, and latency. So I'll go through these first, and then I'll show you some examples of them along with some new metrics. So command bus utilization. So in the memory bus, you have the command bus and the data bus. They can operate at the same time. Okay. Why would you want to look at your command bus utilization when you're characterizing workloads? Well, you want to understand how many percentage of reads to writes do we have. So if you find out, like shown here, that you have twice as many reads as you do writes, well, obviously your workload is not what you thought it was. So now what we can do with the available test equipment is we can make these very detailed measurements, where in the past we couldn't do that. So in a lot of cases, when you were looking at workloads and trying to see what works best for a particular design or memory controller settings, you were really in the dark. So what we can do now is we can actually measure these every single clock cycle for hours and hours and hours and give you a complete and accurate characterization of the memory bus for your particular workload. Now, one of the things you'll see here is this big spike here. This is deselects. So you'll see that the memory bus is the command bus is highly underutilized. And by extracting that data out and putting it in Excel, I can show you this. This happens to be a memory stress test, a Google Stress app. And you can see that 81% of the command bus is deselects or no-ops. Okay, and that's really by design. So the DDR bus, command bus, is really highly underutilized. But the transactions going out on the data bus are underneath that occurring at the same time. So it's not like the bus is not that busy. So you can see read burst length 8, which means there's 8 data beats for the burst length. For this particular application, we had almost 2x the number of reads that we did for write. So it's an interesting metric. On the DDR4 bus, you can also have a burst chop 4, which means only 4 data beats for every transaction. So that would be another interesting metric to see, did your workload perform better with a shorter burst length versus a longer burst length? Maybe you were latency sensitive or you were bandwidth sensitive. You can really understand that now by taking a detailed look at the command bus. So that was the command bus. Now we'll move on to the data bus. What we can do now is take a look at every rank and bank on the channel, and we can even look at multiple channels, and you can get a very detailed picture for your particular workload. How many reads do you have? How many writes do you have? Are they distributed equally among the banks and ranks, or are they all concentrated in one area? Now we're running a memory test here, so you can see it's equally divided between the ranks and the banks, and you can see that the burst length 8 on the reads is almost 2x the writes. So by taking that information and aggregating it out, and putting it into an Excel spreadsheet, what you can really do now with this type of information is really characterize your workloads from a bandwidth perspective. So I looked at an Asus X99, that's where these numbers came from, and I looked at what is the measured performance for a single DIMM per channel versus 4 DIMMs spread across 4 channels. So you got 4 channels, each with 1 DIMM per channel, or 1 channel with just 1 DIMM. So in the 1 DIMM case, all the traffic goes to 1 DIMM. In the 4 channel case, it's spread out. Okay? So what you can see is if all the traffic is going to 1 DIMM, well, the measured performance tracks the theoretical performance pretty well. But when you have 4 channels, you can see you'll deviate quite a bit from that theoretical. Okay? So when you're in that 4-channel situation, yeah, you got a lot more memory, but those 4 channels are going to cause more overhead to the memory controller. And so it's more difficult for the memory controller to reach that theoretical maximum when they have to go across the 4 channels. So that JEDEC spec, and the JEDEC organization is the industry standards organization that controls the DDR specification. So I'm not going to go into too much detail here, but it's basically, I'll just take a look at the first one, read to write, same rank. So the memory controller cannot place those transactions too close together. Place them far apart, but not too close together. If they're too close together, then the DRAM is not ready. The DRAM would lose state, and you would have some data corruption. Okay? So you don't want the memory controller to be tuned to put them too close together. But then again, if you have a BIOS setting or a memory controller setting where these things are too far apart, well, then you're leaving a lot of performance on the table. So really what you want to do is operate right on the edge of the spec, okay? Because latency can be a big deal. So just give you some examples of some latency measurements that I made in the ASUS X99 system, which is a brand new DDR4 system. It's not a server, but it's a desktop. So you can see at the top there, the read to write same rank. So the spec is 8, we measure 10. Well, that's 20% you're leaving on the table, okay? So for this particular system running this particular workload, we can see that maybe there's some improvement to be made there, okay? Some tweaking of the BIOS or the memory controller code. Let's see if we can get maybe this a little bit faster. You can see down on the bottom, write to read different rank. You also see a 50%, okay? Latency there. You know, what's the reason for that? Could we make some improvements there and increase our performance? So now if you're all about performance, you want to decrease that latency, you want it right on the spec. But if you also are concerned about power management, you might take a look at what the intervening transactions are that caused that latency, okay? And in this case, I did just that. So what I could see here, those two writes back to back, yeah, they weren't exactly on the spec. They were 2 clock ticks lower than the spec, but look what he did in between. They closed some banks, okay? So the memory controller went in and closed some banks, and that's good for power management. Okay, so that was a power management move. So now you have to understand, what am I really interested in? What kind of mix do I want for my workload? Do I want just performance? Do I want power management, or do I want some happy medium? So now we can make these types of measurements in great detail. So some of the new performance metrics that we've been thinking about is page hit analysis. Okay, so when the memory controller goes to the memory under control of the workload, they will open the page, then they will write the page, then they will close it. Okay, so the metric we have here is read hit, meaning page was open. That's great. The memory controller doesn't have to do anything else, can do an automatic read. That would be considered a hit. A miss was, the page is not open. Memory controller has to open the page, then do the read. We call that a miss, okay? Same thing on the write case. Now, unused is using its locality of data algorithm. The memory controller said, I'm going to guess, and I'm going to open a page in anticipation of using it. But maybe, you know, under program control from the workload, never went there, so the page had to be closed. The page was open, closed, it was never used. Okay, well, that's not good for performance. Multiple open banks. Well, if you're a high-frequency trader, well, you want your banks all open, right? Because you want to have that great hit rate that we just talked about. Bank group analysis. So for DDR4, what they've done is they've doubled the number of banks that they did over DDR3, okay? But they put some restrictions in. Your back-to-back transactions have to go to different bank groups, okay? Because that gives previous bank group recovery time. It gives the recovery time for the DRAM. So in essence, they want you to stripe the data across the different bank groups. So we can measure that because it's a performance hit if you continuously go to the same bank group, okay? So code that's written to spin on a single location, not good. It's going to take a performance hit on DDR4. So here's some output from running the Google Stress app at 2133. And you can see here some unused at the bottom. So this is where the memory controller guessed and guessed wrong. Okay. What we're seeing here is a lot of read misses and a lot of write hits. Okay. So on the hit from a write perspective, the workload is optimized, but on the read perspective, it's not optimized. Okay, so this is a new understanding as to how we can improve performance of these servers. Multiple open banks, great for the high frequency traders, right? Keep all those banks open. We don't care about burning that power, okay? But we can take a look at how many banks are open simultaneously. So if there are no banks open, well, that means the system is idle, okay? If there's 10 or 8 or 16 banks open simultaneously, well, that means everything's going to be a hit, but you're going to have some serious power consumption, okay? So understanding how often, okay, and for how long these banks are left open can help you do the trade-off between power management and performance. So I talked a little bit about bank group analysis for this particular workload, which was just a memory test. So the same bank group, that's the performance hit path. So you can see, didn't go there very often, which is great. And going to different bank groups on back-to-back transactions, that's the performance case. That's what you see the most of. So that means for this particular workload, where the memory controller did a great job in optimizing and striping that data across the different bank groups. So bank utilization. So this is yet another type of new metric that you can now measure on every single clock edge under any workload situation. So basically what this shows is how many seconds or how many percentage of clock cycles that bank is open, okay? So you can see it's like every fourth bank or every fifth bank going across here. So you might say, you know, I paid for all that memory. Why am I not using it? Okay, so by understanding your bank utilization with your workload going to the memory, you might be able to either make some changes in the code, make some changes in the BIOS or the memory controller code to have better use of the banks. Another thing that this might show you is that you're using one bank too often. There's a failure mechanism in DDR3 called row hammer, and that's excessive activates to one particular location. I see somebody smiling in the crowd. Yeah, you know, this can give you some insight into that. In fact, we do have another mode of this particular tool where we can actually count the activates to individual row addresses to see if your critical applications are in danger of a row hammer failure. So bus mode analysis. So it takes a long time to boot servers, right? You've got all that memory. What exactly is going on when you're booting these servers? And is there any way to make it go faster? Okay, so by understanding all of the modes that the memory goes through, you know, from being idle to active, pre-charge power down, or max power savings, or MPR mode, which is the mode multi-purpose register access, the VREF training, or the write leveling, by understanding how much time the system spends in each one of these modes while you're booting the system is very instrumental to understanding whether you can speed up your boot by controlling some of these modes. So just to kind of wrap up here, you know, DDR memory really dominates the data center, okay? Memory power and cooling consume 16% of the data center's power budget, so we have to be very, very concerned about that. Memory is 12% of the data center's total cost of ownership over a 3-year period. The memory can be up to 50% of the cost of the server. Okay, I was in a data center making these measurements, and I said to the engineer, well, you're running at 1333. And his response was, well, why did I pay for 1600 DIMMs? I said, well, I don't know why you paid for 1600 DIMMs, but I'm telling you, you're not running them at 1600. Okay? Servers are 25% of the data center's total cost of ownership. So by characterizing your workload, you can make smarter decisions and not just blindly throw servers into your data center to handle increased performance. So how did I make these measurements? Well, I'm in the test and measurements business, and what we've done is we have a standalone tool here with a DIMM interposer, and we can put that right into the server running whatever workload. It's invisible to the software running on the server. It's invisible to the hardware. You connect your laptop up to the USB port, and you can see all the graphs that I just showed you. The way we do that is we tap a small amount of current off the bus, okay? So we don't disturb the memory or the memory controller, and we amplify the signal, put it in our box, and we basically track the memory bus clock by clock. So we're a shadow to the memory bus. Now this is per channel, so if you want multiple channels at one time, you need multiple implementations of this, but you know, you can usually get a lot of information just looking at one channel to characterize your workload. So this just shows the system installed. That's an OCP server there that we ran some experiments on. And this was, I think, Winterfell, which was an old one. And what we found was, it was funny, on the DDR3 bus, we could see that the server was turning off the clocks, which is great for power management, but it was only doing it for 7 nanoseconds. So, you know, that's hardly, you know, the going down and the recovery of turning on and off the clocks wasn't worth the 7 nanoseconds that you had the clock shut off for. So you can find some really strange things when you look in detail at some of these servers. So knowledge is king. If you gain more insight into the server and your workload, you can lead to better designs. I'd love to see OCP come up with particular benchmark, you know, like pointing at a piece of code saying, hey, this is a benchmark that we use for OCP servers. Then we can make these detailed performance measurements on different servers and give numbers so you have an apples-to-apples comparison. A workload analysis, what I think we're going to come out with at the end of this is that memory controller settings should be based on the criteria of the workload, okay? You know, if you're Cray and your throughput every day, all day, you might want something a little bit different than if you're Google and you're random read latency sensitive. Can the compilers be made better? Okay, if you are spinning on a single location, you're going to suffer from a performance hit on DDR4 because the data is striped across the different bank groups. And of course, do we need a DDR5? Okay, I work in the JEDEC committees. I'm on several of the standards groups. And let me tell you right now, there's no DDR5. Okay, not right now. We have a DDR4E, okay, which is on-die ECC, has some performance enhancements. We have LPDDR4 and we have LPDDR5. Okay, but right now there's no DDR5. So with DDR4, you're probably going to have it a lot longer than you've had DDR3. So you've got to be able to really measure things in great detail and squeeze every single bit of performance out of that memory bus as we possibly can. So this is my contact information. If you're as excited about memory as I am, you can contact me, and I'll be happy to talk. So are there any questions? Okay, great.
So when you find somebody who's got higher performance system is running, you know, 1600 versus 33 or DDR4 and something.
Yeah, DDR4 can go all the way to 3200.
Yeah. What do you see, you know, if the people who have the boards, they want to go off and they want to do that? They have to go through a lot of rules. They have to go through a lot of changes back to the vendor's BIOS, all this sort of stuff.
It really depends on the flexibility of the BIOS. For example, our Asus X99 board, it has, in the BIOS, it has a tweaker mode. So we can go in there and tweak, and get that thing running up to 3200, literally. Okay, now we see loads of JEDEC violations, okay? Because now, you know, what's the DIMM rated to, what's the memory controller rated to, and is there a match there, okay? So that was another thing that I was doing investigation on, is are the memories too conservative, okay? Can we run these memories from a latency perspective a little bit faster than what they're telling us that we can, okay? Because that can be a big performance improvement. But by and large, you can read the SPD, and we do that with our tool. We read the SPD so we know what the memory is capable of. Then we go into the BIOS. Usually it has a tweaker mode. Jack it up. That's how we do it. And, you know, in a lot of cases, we will violate the JEDEC spec and we won't see any memory errors. But then again, we're only running for a few hours. Okay, I know that the data centers see a lot more memory errors than they should. Okay, and there's some, in my circles, there's a famous Google paper, a couple Google papers written on this. What I think is happening is these are design flaws. Okay, signal integrity, memory controller settings by the BIOS, putting those transactions too close together. So we have that trade-off. You know, do we push the spec, or do we back off in favor of being conservative from an error perspective?
So when you push it harder, when you push it beyond when you start seeing errors, you see like one or two errors, or does the whole thing fall?
You know, it really depends. We've seen, what we usually see is when we push it, we'll see like a burst of errors. Okay, so it'll burst. If that interferes with the instruction set fetch, down it goes. Okay, you know, if everything's in the cache, right, and it's just pulling data that it's comparing, you know, it could run and just get memory errors. Okay, but as soon as it starts to do that instruction fetch, boom, goes down. So any more questions? Okay, great. I'll be around all day if anybody wants to have any more conversations. Thanks. For the gamers. Well, when you're a gamer, you don't care the rest of the Hi.
Barry Wood from IDT.
Oh, how you doing?
Not bad yourself.
Good.
So I'm not with our DDR4 memory product, but I do not very
Oh, yeah.
somewhat familiar with the product.
Yeah, we did a RefIO. We have a RefIO tool. Yeah, great. Yeah. So I think IDT, you guys have some of our logic analyzer based tools. Yeah. But this is a standalone tool. You know, so it's, but we only have to do the address command and control in order to get all those performance metrics. So.
Yeah, in the room. Yeah. I remember I was telling you.
Well, like we had now with all
It's fine.
You think they need it? Oh.
yeah, just because they're have that.
Okay, that's one.
Oh, do they want me to come? Can I find you? Because I want to. You might want to come over to.
I probably want to come over.
It is good. Can you hear me? Yeah, seems to work. Yeah, that's great. Okay, I'm going to introduce you the DAP projects. Oh, that's something we call the data center as a PCB. That's based on an Express Fabric. So the Fabric is a PCI Express switch with multi-host and SRIOD. So virtualization access to PCI Express port. So roughly the connectics for that Mellanox introduced to us this afternoon should be able to work straightforward on this design. So just a quick background on the project. So this is a project we started in June 2014, and we wanted it to be a community project. And we want to release specification and design as well as implementation. So meaning that the goal of the project is to release Gather files, schematics, everything needed to produce the board in productions from the community. And I think this might be one of the first projects running in that direction within the OCP community currently. So the project is designed in collaboration with OCP community members in Europe. So currently mostly in France. So if you speak French, it might be easier for you to be introduced by the project, but we speak English. So we try to improve our English, just to let you know.
What is good is that we have corporate sponsorship right now. So as we are designing hardware, one of the key elements is to find a way to finance the prototypes and finance the debugging tools. So Thales, which is a big defense company, has started to fund the project back in December 2014. And I will explain you a little bit more further what we are doing with them. And Horizon Computing Solutions, which is my company, is also sponsoring that project. So we are providing tools and development for the system. We have two sponsors. There is a third one which is coming up, but I cannot disclose the name of the sponsor to Google. That's another big company within the defense market. So Data Center as a PCB is a project which aims to design a PCB which can run up to 35 Celsius degrees, share any expensive features I/O ports. So we think that 100 gig Ethernet ports needs to be shared between multiple CPUs, and remove as much as possible cablings, and increase the CPU count on the same PCB. So that's the main goal of the project. But let me get back on the key things from this project, which is how to work together. So we said we have a couple of community members working on the schematics and the Gerber files, as well as mechanical drawings and everything needed to design a system. And the main challenge was what kind of tool can we use? So GitHub is a good tool for source code sharing, but it's not very efficient for mechanical file sharing and so on. So we started to work on a VM, which is providing us the backend infrastructures to design a system all together with people spread everywhere in Europe and working within a major corporation. So that VM is incorporating some open source software like Open Project, Sogo, to provide email infrastructures for the project members. We do have also web servers for sharing files and cloud storage. And what is key to us also is to have a 3D web VM layers where people can have a look straightforward to the mechanical drawing of the board and the chassis that we are going to design for that system. So this VM is still under heavy development. You can join the development team. This is something key to us, having the right tools to design systems. And you can have some example about the VMs by going to that.pshare.com or ruggedbound.pshare.com. That's two websites which are powered by the VMs we are working on. So if you want to participate in that project, as this is a community project, here are a quick drawing of the tools that we are using. So to run the schematics and the layouts, we are using a tool which is called Aperture. So it's not Altium Designer or ORCAD or any other proprietary tools. We use Aperture. That's because it does have a web interface. So we can work as a team on the same design files using just the web browsers. It's available on Linux, Mac OS, and Windows. And what is really good is that it's free of charge for open communities and open hardware communities. So the Aperture was not supporting the Open Compute license up to the time we contacted them and decided to use their tools. So they have added the Open Compute license within the files, so we can use their tools for a while. The other things was how to communicate on what we are doing. So on the top right of this slide, you can see the websites of the DAO projects. So we do have a website explaining what we are doing and trying to get traction from new developers. That's key to us. So explaining what we are doing, why we are doing it, and where we want to go. This is where we are sharing our ideas and where we want to drive the design. And on the bottom left side, you can see a rendering of what the first DAP chassis might look like. So this is using pure WebGL, so you can browse the 3D through your tablet. I was going to say the iPad, but I think it's better to say the Surface Pro 3. So that's using WebGL. The idea of that tool, which is fully written in JavaScript, to
is to have the capability to put some command directly on the various mechanical parts while you are looking at the parts, just to share your comments with the development teams and have something very interactive with the team. This is the 4 development tools that we are using. They all have their limitations currently, and that's why we slowed down the development of the DAP project. So last year when I presented it, our expectation was to bring up across that model board for this summit. And this is not the case only because we didn't face engineering issue, but we faced tools accessibility issues. And it took us a huge amount of time to set up the right tools to have the team working all together. Just to let you know, the DAP project right now is a project which is driven by 30 people. So it's getting bigger and bigger, I would say, not every day, but every month. So that's quite good. We have engineers from Thales, from Imagery, from my company, and from various IT companies who are joining the projects as community members, and that's really key. And this is why we are working really hard on the tools. So if we don't provide the right tools, you cannot set up a community. This is really something that we are dealing with. Just to get back on the project, and that's perhaps some slides, but to run up to 35 degrees, so we are targeting that project using only mobile chip technology. So, which means we are more interested by the processor sitting inside your laptop or sitting inside your tablet, except that we want to have ECC support, so that's key to us. And hopefully some chip vendors does support ECC on mobile chips. So EMD and ARM are providing some of that technology. Intel still doesn't, but it might be happen within the next couple of months or next year, I don't know. The key point is that they have a higher junction temperature, and that's really good when you want to run a higher temp. And that's why we are using them. And they are also optimized for power management. That's also good. Just to get back on the fabric, so last year I was telling that we were working with PNX, so PNX becoming available. The chip was not tape out, it's not tape out, and we received our first samples. So we are working on the fabric firmware right now, which is running under Linux. And it's going to be a formal product launch in May 2015, so in about 3 months from now. That's a really interesting fabrics topology. So we do have TCP/IP working on top of the fabrics. We have a Virtuos, which is working also on the way we started to work on the SRI of the firmwares and setup of the fabric, and that's the key point. The key things is we use PCI Express because it's free of charge, so it's available mostly within any microprocessor. So you cannot remove it. That's the standard I/O used on CPUs. While NIC, Ethernet NIC, costs about $300 US. So sorry for the maintenance people, but the main idea is really to share the I/O subsystem. So we are soldering down everything. So using mobile chip as another key advantage is that the footprint of the CPU is much smaller than the footprint from a server part. So meaning that within the same area, we can stick much more computing resources than with the server part. And this was also a key thing. And this is using EGA, so we have to solder down the CPU and the chipset. And this is roughly exactly like putting a bunch of laptops on the same PCB. So from the management perspective, so I know there has been a lot of debates around the remote management systems. So we decided to kick off our own management systems and to get rid of the VMC things. So we do not have any VMC on top of the board, but we have a specific remote management board which is running a Linux operating systems and which is implementing Microsoft REST API. So we don't support IPMI commands, but you can get access to the remote management board for the REST API from Microsoft. We think it's far good enough. We have a web client, we have a CLI client, and you can get access to the remote management portal through that API. That's easy to put in place, and what we discovered is that most of the students getting out of universities knows REST API, but doesn't know anything about API. So that's the main benefit of using REST API. You can find new resources and fresh resources pretty quickly. So, just from an architecture perspective, we didn't change anything from last year. So we are still putting 12 CPU on a single PCB. They are linked together through PCI Express switch. They are all single pieces, in fact, using ECC memory and booting their own operating system. We decided last week that we will be sharing the NVRAM and BIOS for all the CPUs. So meaning that when we will upgrade the BIOS, we will upgrade only 2 NVRAM chips on the board, and these chips are going to be shared between all the CPUs. So there has been a big debate inside the community regarding that, but we think it's far much easier to update only 2 NVRAMs rather than 1 NVRAM per CPU. So we are going to support SRIOB on the network controllers with dual cards access, and then that will be based on OCP mezzanine V2. And the remote power management module is right now available as a demo unit on Horizon Boost, so you can have a look at it for, on the shelf. So just from a remote management perspective, this is what we decided to implement, and this is what we have done. In fact, so right now it's not working as a 12 access to the CPU. So we have the first demo unit is working with 4 nodes. So we will expand it to 12 and 16 within the next couple of weeks. So we tape on the first board with only 4 nodes. So we just wanted to be sure that everything was properly put in place. So we do have everything at the bottom side working. So we do not have yet the ITVM module based on H264 real-time video encoders. So meaning that the console has to be serial up to now. So, but we will be supporting graphical console during several timeframes, something like that. What is really good is that last year I was presenting a dream. So currently we are starting to have running hardware, which is far much better. So regarding the firmware, as I said at the early stage of the project, we want to have everything open. So we decided to open the firmware. So everything will be published, including the content of the EEPROM running on top of the system. And we will be running core boot, and that's really good that EMD is providing us support for the core boot on that system. The management node is going to run under Linux and using the REST API from Microsoft. So we rewrite the API with Python or Python. Sorry for my French accent, I don't know how to say it in English, but that's the scripting language.
Python?
Yes. You're far much better than me in English. Thank you. So the PCI Express Fabric configuration firmware is currently under active development, and we will set it up under GitHub next week. So the firmware management system is right now available on GitHub/Rackpad. So that's the other projects we are working on, but we are sharing the same remote management module, and you can participate to that development. We have quite an active team working on that. So just to show you, this is what we have done with the web client. So it's using the REST API from Microsoft, and we do have very basic implementation. But for the 4 nodes, we get access to the remote console through JavaScript, DT100 emulators, so we can get access to the power management of the systems. We know exactly how many watts the system requests, and we do have the states of the servers, like on/off, reboots, resets from the motherboard. So you can see that running live on Horizon Boost. There will be Maxim on that booth. So Maxim is not one of my employees. So we did sponsor his travel to that show, and he's part of the community in France. He was a student and deeply involved into the development of that project, and we thought it was really good for him to come in. And he's there during his vacation time, just to let you know. So that's the main benefit of being French. We have a lot of vacation. So we can come to, to this kind of show during our vacation time. From a cost perspective, nothing has changed since last year. So we are still targeting sub $600 per node. So that's the main benefit of using PCI Express Fabric. So we do not have to add any Ethernet adapters. And we are still driving the fabric with more than 300 gigabits per second available on the PCB. So we are targeting 384 gigabits per second for the 12 nodes. So that's very high level of bandwidth, and that's really good for some workload, especially if the one who needs to share data is being computed out. So the total power per server is about 60 watts. That's not a lot, and that's because we are using the mobile technology, and this is how we can get that systems. Initial nodes power is scheduled for that summer, around July. We have concluded the schematics. We started the layout 2 weeks ago. So if you go on Inverter, join that project, you can get access to the full schematic of the system. And you can join the team or request to join the team. So everything is open, but you cannot change the design without being part of the team. So the first step is to get in touch with one member of the team if you want to participate in the design. That's only because when we open everything, so we got people changing the design without informing us, and this was a big mess. So we took back the control on who can write up inside the design, but we are very open, so everybody can participate. The hardware is released under the OCP license. The software is released under GPL v2. And regarding Thales, so the project is for defense, mostly aerospace. So they are sponsoring the project to validate that the PCI Express fabric can be reconfigured in a very quick manner, and they are mostly sponsoring the firmware development of the PCI Express fabric. So, is there any question? Yeah.
So the open source files that you start with some sort of code base, some sort of open source base, or
yeah, we started from the Cloudboot open source firmware, which is available on the web. Cloudboot. Yeah, Cloudboot. Yeah. So we started from that, and then we read a lot of the documentation from UD just to set up the proper registers and so on. It's doable.
Have you ever built a prototype using the PLS Alpha switch?
Excuse me?
PLS, you are using the PLS single IOV switch, right?
Yeah.
So they have the Alpha switch. So before you build a prototype, I mean, can you try to build with that switch as a initiative to build a prototype before you design this board?
No,
yeah.
Yeah, that's Catenato switch.
Yeah, but
this is the one we are using.
They have the Alpha switch. Can support similar function, right? So before you build this board.
Yeah, we tested the switch, in fact, from the FPGA implementation that they had. So we got access to the FPGA implementation they had, and so we thought this was the right way to go and to move forward. And we followed the projects even during the merger, which has been a little bit disturbing to us. So the team has to go to Avago, and so it delayed a little bit the release of PSX, but right now everything is on track.
And so why you pick a 12 node?
Because when we look at how many nodes we can put on the PCB, we say, okay, we run the mechanical layouts and say we cannot go further than 20 nodes. So this is roughly PCB size constraint.
Yeah, can you think about the port tolerance or the dual port support? Right now, for each node you have I4.
Yeah, we don't have any fault tolerant functions on the board, so that's really cheap hardware. So the idea is when one node dies, we shut it down and we don't use it anymore. So that's perhaps wasting things, but we think it will be reliable enough to run that way.
Looking at your architecture, sharing that IO resource over SRIO seems like you would need to do a whole lot of mutual exclusion between each of the processors to send a message or receive something.
Yeah, that's part of the Capillate2 firmware. Yeah, that's implemented at the switch level, and we have right now 4 nodes with one switch and one board, which is working fine. So sharing the same board, we still are facing some performance issues, but from an implementation perspective, we see that it could work, and we are improving the firmware, and we are trying to understand how to improve the performance. So roughly on the 40 gigs, we reach about 10 gigs then. So we are around 25% of the global performances, but we are not really worried about that. So, and you know, that's people are working on that time, so that's not a traditional engineering project, and we work during the weekends, and there's still a lot of bugs. So if you want to join the team, you are free to come. And we are always seeking for new developers, architects, and so on. So that board is going to be used in production from Thales, and we also have a cloud provider in Cambodia who is really interested by that technology because of the cost of the system. The key things to them is, you know, Cambodia is a really poor country. They don't have a lot of money, and the global cost of the solution to start up a cloud provider is about $5,000 US. So you have to figure out how you are going to provide hardware within that envelope. And it seems to be a perfect match to them right now.
Question again with the fabric. If I understood correctly, you've got the 12 drive sharing one external interface port, so you're not speaking to express outside the box.
Yeah, right now it's speaking Ethernet. That's because we want to put that board into a rack part chassis, so which is an outdoor computing solution. So I think it's a perfect match. And we want to get out of that chassis using Ethernet. So that's we could use PCI Express. One of the key issues is we didn't find the right retimers and the clock buffers to go long distance. So, and we didn't want to take too much risk on that. So that's why we compared to Ethernet. It looks like much more easier to run.
And so for peer-to-peer communications, how do you support that? You go all the way out to the Ethernet fabric and back?
No,
we support peer-to-peer work.
We're using peer-to-peer communication on PCI Express. So we do have a Linux Ethernet drivers on top of the PCI Express fabrics. We didn't check on Windows. Okay. I'm not even sure that somebody did try to make it work on the TCP/IP stack, but I think it could work. So it's working on Linux, so there's no reason why it shouldn't work on Windows. Except that it needs some developers to check that it works. Yeah, you just need somebody to work on it. So. Oh, thank you for your time.
Thank you.
Thank you. I think this is the end of the day.
Yeah, this is the end.
Should I say that?
So tomorrow we start back at